of their suggestions.
We are live online, coming to you from Woods Hole, Massachusetts, where it's another lovely day for any of those of you who are sweltering in Arizona or Texas. So this morning, you can see the agenda. We're going to have a little bit of Nathan and I trying to make some kind of synopsis of the discussions from yesterday, and see what thoughts the folks here have and online. I guess with the online, Sam, maybe it might be, if people raise their hand or something, is it easy to put people up there right now, or can you at least unmute them? Yeah. Okay, all right. And then we'll have Jimmy and Malcolm are then going to run the next series of talks, which are some mini talks on sort of the international view of observations, and then 2 invited talks. Again, we were kind of model heavy yesterday, and then this morning is going to be a little observational heavy. So we're going to have WHOI and Meghan talk about both satellites and in situ and observations specifically, and then some more lightning poster talks, and then after Meghan, that's the last actual talk that we have for the workshop. Okay, the rest of it is breakout time and discussion time. So again, that's really what we want to focus a lot of attention on. So Nathan, do you want to stand up by me, or would you rather sit there as we try to put together? I actually made some notes on PowerPoints, but as some of you heard me say, the minute you put up a PowerPoint in a group of scientists, it becomes like set in concrete that people then must discuss the wording of. Whereas if I just say it, I can make it sound exactly as equivocal as I really do mean it. A bullet seems very definite, but just me saying things, and All right, so I tried to step back and say, what are some things that we want to do better at sort of the broadest scale? Okay. We'll get into some. There's the overall, what do we want to do better, and then there's all the what do we need to do better to do these bigger things better. All right. So that's part of it, is I'm just hoping by the time we get to the end of it that many of the things that were really specific things that we talked about last time sort of fit within the larger context. So one thing that I heard that came up, right, was the idea of improving our S2S predictions, sub-seasonal to seasonal, as perhaps a focus of things that we could do. So that's what I'm saying, very, very broad, right? And also in that, I also heard we would like to do better East Coast storm predictions, okay? And that can be extratropical, tropical to extratropical, or, just nor'easters, the whole so sort of local weather-ish, but then, and S2S. Okay, I'm waiting for someone to leap up and go like, oh my God, no. There were ways that we connected through to climate. So Jamie, said, carbon, measuring carbon as part of this is immediately a link to climate, types of questions and some other things. But those were sort of the 2 biggest pieces that I heard out of the talks and the discussions yesterday. Yes, okay, so, all right. Do I hear a second? No, and we can come back and revisit all of this. This is just trying to sort of put this together. I then said, again, and now I'm being even more equivocal, there was some coalescence around the idea that atmospheric fronts and storms and their interactions with the ocean might be important to S2S. Okay, it's a discussion about that, discussion about the level of importance of that, but you know, so that if we want to do the S2S predictions, then that getting that piece right seems to be something that we might want to think about. Okay, so then that gets us to, like, what do we need to know? And there were a lot of things that we talked about that we need to know, but here are some things. I think we need to know, how do the ocean and the atmosphere actually interact at these higher resolutions? Like, realistically, how do they interact? From observations, right? We have hypotheses from the models. Not all the models have the same, you know, the same interactions, the same feedbacks. They have different results when you get to these higher resolutions. I think we have to ask ourselves, really, how do they interact? I'm still struggling to understand what are even the key scales for observations and modeling. You know, I think there was a lot of discussion about sort of the atmospheric front scale, sort of resolving that. On the ocean side, ocean mesoscale, and then I've heard down into the submesoscale. And I'm still a little unclear when we get to the submesoscale, if it's just because the higher resolution we can go, the happier we are, or if we really have a sense that that must be resolved. But that's a question that I would you know, explore. What are the interactions across the scales? That's sort of a question. I said, I don't think we know very well in like a Gulf Stream kind of region. What's just I said the background air-sea coupling, let's say the non-perturbed, not when a storm is coming through. Okay. What are the dynamics and thermodynamics that create and sustain the ocean and atmospheric boundary layer structures that we see? Actually, we haven't really even seen them. So, but when we do see them, because we're going to observe them, what creates that, right? So the non-storm, sort of the non-storm conditions, and then people, you know, talked about then we need like case studies of storms, so we need to have a number of observations of storms as well. But I'm just saying, I think there's still a lot of open question about just what's happening in that coupled system when there isn't a storm going through, right? And Jimmy's group and you know, other groups mentioned this too, but you know, even the observations that we do have we tend to have a focus on dry, or the modeling tends to have a focus on dry, and moisture is a really, I mean, it's not a front, it's not an atmospheric front over a forest. It's an atmospheric, even that has some moisture, but it's an atmospheric front over the ocean. Like the moisture has to be really important. The moisture profiles within the atmosphere, the clouds, all of those pieces, we need to make sure that we are observing the moisture components and talking about those as well. Waves and their role, right? And I guess I could say waves and currents, but you know, so I'm sort of thinking of that upper ocean piece of it. And then I would say another thing that we don't know about the interaction is we don't know, I don't think, very well at all. I've now made it sound like we know nothing. I was not going to start with that. What are the air-sea exchanges in regions of highly inhomogeneous surface conditions? I think the bulk flux parameterizations, and we can have a conversation about, you know, under sort of mean conditions, right? That's one thing. But what does it mean that when we do a bulk estimation of the fluxes and we're taking 10-minute averages of air that's been flowing across SSTs of, you know, in that time, degrees difference, right? I just don't think we understand the exchange at those scales. I don't think we understand how our bulk flux parameterizations should be adapted. I'm not sure we can use them when we come down to that scale, because that makes assumptions that I'm not sure are accurate. So this is all part of the, just like these are just some things that people have talked about. Were there others that people talked, I'm just trying to think, others, yeah, about like how do they actually interact at high resolution, right? These.
Yeah, and there's always someone further to one side that says, well, actually, and then, they added, a whole new scale that you hadn't considered previously. So setting a sort of, yeah, right.
Out of the cosmograph.
Well,
yeah.
We need to consider quantum effects,
Yeah.
But, no, I think that setting a reasonable minimum standard resolution and saying, we'll be happy if we at least get to this point, because you can always go a step further. There's always a false bottom in physical processes. You can always resolve more. And then it's an exercise in CPU hour waste.
Yeah. So I think, yeah. So that's a really good way to frame that, is sort of what's the minimum resolution of observations and modeling that we would need. And I think we have a slightly better sense. I mean, people were, especially Justin's group was, really talking about resolution and, various resolutions of both the atmosphere and the ocean. But that still needs to be discussed. And then, like on the observational side, is it the same? Do we just say it's the same on the observational side? I would say another of the what do we need to know, so moving us away a little bit about the actual interaction, is I think we need to know a little bit more about by what mechanisms and under what circumstances the marine boundary layer influences the free atmosphere, right? Because that's where we get into the S2S, right? When is it venting, right? What is it venting? What causes the growth of the boundary layer, right? How does that working? I also put in there, how do submesoscale ocean frontal process dynamics work in these regions of fast currents? So what are the small scale ocean processes that may play a role in this that we haven't really observed yet? So, and then I put in, and Larry stated this very nicely, the impact of mesoscale and submesoscale eddies on air-sea interaction, and I would put that sort of into the interaction of the ocean and atmosphere sort of at these scales, but with a focus on the eddies. Other things that I heard multiple groups say, what are the most important metrics for various things? And it was metrics for what's the suitable resolution that we need in both time and space for actually getting to the answers for some of these things. Other people wrote it as we need more process-oriented or feature-based air-sea interaction studies to identify the correct metrics for assessing individual component interactions. What are those? And I haven't heard any clear consensus at all on what might the metrics be. So, which are kind of important because that kind of helps us also get to observations, right? If there's a really key metric, for instance, I'm still really fascinated by Reese's, height of the tropopause and the depth. I don't know why one says height and depth. I'll say height. Height of the tropopause and height of the marine boundary layer, right? And I was making that a little analogous to when you're thinking about deep convection in the ocean, right? And you're looking at, you're in a region where you've got the right circulation so that there's a doming of the isopycnals, right? And then you've got a storm comes over and you mix the mixed layer down, and then the key things happen when those interact with each other. So I'm presuming that this is somewhat analogous in some ways to that one. But that's a key number. Or let's use the barrier layer, right? That's a metric that we care about in the ocean, right? What's the mixed layer depth and what's the salinity, layer depth? So if those are important things, then those are things we should measure, right? We should find some way of measuring those, because if those are defining characteristics, then we should measure them. So we need to come to an agreement on how to define these. We need to figure out what the critical mass that we need to observe the variables that we've decided. Where would we put them, right? And then some other things we can talk about, like, what types of models, LES models, or, improved exchange physics and some other things like that. So We have 50, that clock is wrong. We have 50, like, that cannot have taken 3 minutes. No, it did not. So we have about 15 minutes. And so I know, I'm sorry, we just kind of threw a lot of stuff out there to think about. But is there something, this is your chance to go at this point, thinking about it, is there something we've really missed in this? So Jimmy.
Yeah, so on the S2S side of things, it seems like one thing that didn't come up that probably should is, what are the processes within the ocean that we don't fully understand for the evolution of the SST? Because if we're talking about, we want a month's worth of very good information for the evolution of the SST, and that's not just what is the PMEL doing in the atmosphere, but also what are the processes in the ocean that are going to really play a big role in the time of evolution of the SST, because what we saw yesterday was, on these time scales, the ocean heat flux transport matters.
Yeah, and I think I lost that a little bit with getting into the sub-mesoscale and mesoscale eddies and so forth. So I think that's good, because I did mean to include like the ocean component in that one. So trying to write this down. So just make sure the processes in the ocean that influence the interaction on key S2S scales are observed or understood. Meg?
Yeah, following up on Jimmy's comment, some of those processes may involve like the very deep ocean. So your summary, which was very well done, focused mainly above the ocean, from the sea surface to, top of the tropopause. But to get the S2S, the eddies and the rings and the meanders of the Gulf Stream and the position of the Gulf Stream, we may need to know what's happening at the bottom of the ocean. And,
yeah.
And the interactions with, say, seamounts and bathymetry and, topographic Rossby waves and all sorts of stuff like that.
Yes, thank you. Yeah, because I didn't mean, I meant to make it what's influencing sort of the Gulf Stream and the structure of the Gulf Stream in that one. I think it would be an interesting question to ask, how much do we need to know of various things if we wanted to do, say, a 3-month forecast of the Gulf Stream evolution? Right? What would we need to measure to do that? How far away, how deep would we have to go, right? So I think that's one way that sort of framing this in sort of the S2S kind of thing, say what is the time scale of evolution of the ocean that we need to get, and then what observations and modeling do we need to have in order to have that piece of it work well? So thank you, Meghan, because yeah, I definitely didn't want to leave the impression that we definitely need to be thinking about the evolution of the ocean in this. I think I focused a little more on the atmospheric boundary layer because truly, I think we have even fewer measurements. I know it's hard as oceanographers, we're very tied to the fact that we have nothing in terms of observations, but when you look at, which I've done before, a map of where we have actual, not from island, which is a perturbed boundary layer, right, near the surface, but from ships. Like, whole swaths of the global ocean has never once had any kind of a radiosonde within a 5 to 10 degree box. I mean, we're picking, this is great. We're picking problems that are totally data poor. So, Andrea, did you raise your hand? Yeah, is the mic? Oh, thanks.
Yeah, hi. From the perspective, again, of the seasonal or subseasonal to seasonal, so these predictions are ensemble in nature. And so in addition to understanding the processes and being able to make a better prediction, an important piece of it is to be able to get the perturbations, the correct perturbations, so that the error grows. right? If you're not doing a good perturbation, you're not going to get a good ensemble. And so I'm wondering, in particular, if this group could think a little bit not only how to make a better prediction, but how to figure out what's going to grow faster in terms of error, in terms of things like that, because it's a very important piece of these ensemble predictions is how you get those ensembles going.
That's really fascinating.
It is.
Yeah, no, is that a combination of observations and modeling? Is that like we need some modeling analyses to explore the parameter space? Is that a combination?
Sorry, so we're really good at this in the atmosphere of understanding the processes well enough to understand which modes are the ones that are going to grow. So I think we may need the ocean observations to understand, you know, if the Gulf point of separation is the key to this. We need observations of enough instances of what happens at that separation point to understand which ones grow and which ones don't. And so I think it's a lot of observations that we need first.
Okay. Cool. That's really interesting. Sam, is anyone online raising their hand? Okay. I don't want to leave any one of them out.
If the goal is to have a 3-month forecast of Gulf Stream position and dynamics, how much of that depends on the loop current, Florida current, loop current, Caribbean dynamics? That's a genuine question. I don't know, but you know, is getting the surface fluxes in the Atlantic Ocean going to be our panacea, or do we need to go further upstream to look at those dynamics? And if so, what scale?
And it's totally fine for someone to say, we know that, like people know that, and you guys should just go look it up because it's sitting out there. That's a fine answer, right? It's also a fine answer if the reason that we're not answering that question is because we're not quite sure what the answer is, and we don't know that anybody does know the answer to it. But again, it's totally legitimate for you to go. Literally every oceanographer on the planet, except apparently the two of you standing up there, know the answer to this, and then tell us what the answer is. So feel free to just throw out answers if you have them. But are there key processes or things that we've missed in this? I mean, are there missing pieces?
Having spent time in the ASR ARM program, it's hard for me to talk about climate and field campaigns without aerosols ever being mentioned, and they didn't come up at all. And I was searching now to try and find, there was a field campaign recently where they were flying over the Gulf Stream down before it separated. I don't know if anybody else is familiar with that field campaign.
What's it called?
That's what I'm trying to
Oh,
track
okay.
down. Right. So I learned about it pre-pandemic, and so now I'm like trying to search back for it. But the point is that there is motivation from the atmospheric science side for looking at the Gulf Stream for another reason, which is aerosols and activation of clouds.
Yes. So I think we should make sure that we're putting in the exchange, sort of the exchange, that we're not just talking about heat or moisture or momentum, but there we put in, you know, sea spray to create CCNs for clouds. I mean, and so yes, so that's definitely, I mean, and that would go as part of the moisture as well. Like if we're worrying about clouds, right? That would be a role as well.
Roger, do you want to unmute with your question?
Oh, good.
Oh, sorry, I was just going to make a comment. Something that came up in my mind yesterday is that I haven't heard any reference to the Fascinex experiment, and I don't know if anyone remembers that, but it was a subtropical frontal air-sea interaction experiment quite some time ago, but it had a lot of components, including some aircraft and small scale ocean variability. And I wonder if it's one point of reference that we might use in thinking about this and scaling it up to the Gulf Stream region. It's, climate mode and some other things in the Gulf Stream were certainly mentioned, but maybe this belongs in the discussion too.
There's nods around the room about FASTNX. That's definitely true. Yeah, frontal air-sea interactions experiment.
It was led by Bob Weller.
Yep, that's right.
Justin, do you want to unmute and add something?
Oh, and John's got something too. Okay.
On the same theme, John Bain was on our group yesterday, and then he had internet problems and he left our group early, but I think he was involved in field experiments in the Gulf Stream in the 70s and 80s. So it might be worth talking to him. He did say he'd try and join today. Gale was the experiment he mentioned.
He's on and his hand is raised, by the way, Justin, so just...
Okay, so let me stop right now and I'll pass it on.
John, do you want to chime in here?
After all that buildup, if we can't get him. You're muted, I think.
How about now?
Oh, we can hear you now.
Good. Yes. Thanks, Justin, for mentioning that. I actually was on a couple of FASTNX flights in the 1980s. Carl Freehey and others. At the same time, using some of the same aircraft, Navy and NOAA P-3 aircraft, we conducted the Gale experiment off the southeast coast of the U.S. And the oceanographic group in Gale measured the Gulf Stream while numerous atmospheric measurements were made, largely with aircraft, but some with ship and remote sensing and so on. So there's quite a bit there. One of the things that I wanted to mention today, in addition to reminding us about these earlier studies in the region, I would be very interested in hearing some discussion about the atmospheric jet stream or jet streams. Arno gave a very nice presentation yesterday. This really got me thinking about it this morning, thinking about a 3-month forecast. The jet stream plays such a role in generating and guiding the extratropical cyclones, which are one of the major forcings of the stream, especially in the cool season, but throughout the year. So we will presumably, for a 3-month forecast, need to know what the jet stream is going to do for 3 months. I think of them as the weather waves, the jet stream, sort of 3 to 7 day period waves that propagate eastward in the jet stream that generate and guide extratropical cyclones. That's fairly well known. One of the things that is overlooked some, I think, are intraseasonal oscillations of the jet stream. If you look at if you filter out the weather waves, so do say a 10-day low pass filter, and look at what the jet stream is doing, it will move north and south in the intraseasonal band, 10 days to 100 days. And it can have a major impact. A case in point I'm thinking about is the bomb cyclone Grayson that happened in January of 2018. That spun up off the southeast coast of Florida over the Florida current, warm water there. But the jet stream for about a week or longer period was at a very low latitude in comparison to much of the rest of the season. And because it was down there and a weather wave happened, it probably played a key role in generating that cyclone, which then moved up along the Gulf Stream all the way to Cape Hatteras and beyond, and became, I forget the lowest pressure, but at 960 or something like that. I mean, it was almost hurricane strength by the time it passed Cape Hatteras. So there are these episodes that are related to the jet stream, and I just wanted to put in a word for making sure we don't overlook what the jet stream is doing and what the forecast challenges are for the jet stream.
Thanks, John, because I think that's kind of analogous to our questions about the Gulf Stream, like, you know, where are we at in predictability of a few months, you know, for that sort of guiding feature. So thank you. So that's, obviously there's a lot more discussion time in the schedule today, but now we're going to turn to Jimmy and Malcolm, who are going to get us going.
Okay, I'll introduce Malcolm Roberts, and he's going to give us an update on some of the work he's been doing. So yes, slightly not as advertised. So this is very much modeling, because I'm very much a global climate modeler. But hopefully Larry and Hyodae will do the observations bit of this half hour. It won't be me. Okay. Okay, so yeah, so I was just going to talk a little bit about mostly European perspective of global high resolution climate modeling in there. Some of the things you've already heard today from, yesterday from the posters and things, so I won't kind of dwell on them too much, but I was kind of collecting some material from a few of European projects that I've been involved in or I know about, and then also a little bit of international via the HIRIS-MIP work. Oops. Okay. So yeah, so I've got to mention EU Project Primavera, which finished a year and a half ago that I was lead of. And then there's a couple of, there's an ongoing European project, NextGems, which I'll talk a little bit about. ERIE project, which will start early next year, which I kind of co-led the proposal. And then HIRIS-MIP. And so a little bit about HIRIS-MIP to start with. So HIRIS-MIP, we were a bit disappointed, I think, with CMIP in terms of how they were developing model resolution and the processes. So we developed a very simple experimental design for CMIP6 HIRIS-MIP. So we had a very simple atmosphere-only simulation design and a coupled simulation, which was much shorter, kind of enabling more groups to run the simulations. And then the idea was to try and aim down to about 25-kilometer resolution and look at what the impact of resolution was on all the processes that we were interested in global climate. And just to get this kind of, just to give you a picture of where we're coming from global high resolution modeling community. So on the left there is the CMIP6 deck. So that's the kind of standard CMIP6 type resolution type experiments. And those are the resolutions that were in CMIP6 that are the main feed into the last IPCC. So you can see that for the most part, the ocean is 100-kilometer resolution. So on the x-axis, and on the y-axis, the atmosphere resolution is, you know, sometimes 100-kilometer, but sometimes 200-300 kilometers. So that's kind of where we are in terms of the models that go into IPCC. So HIRIS-MIP on the right is where we were trying to push towards. So I guess I should one note. I guess this one down here is IHESP that Ping Chang led. So that was kind of with an Eddie Rich model that ran, you know, multi-centennial simulations. So there is kind of one bright spot on the resolution. But yeah, so the HIRIS-MIP, so we were trying to push the resolutions from 100 kilometers down to 25 kilometers, and then the atmosphere kind of similar. And I'd say try and look at what the impact was on climate. Kind of Primavera and HIRIS-MIP, we had a few papers that were related to kind of Gulf Stream and air sea interaction, but this is just a kind of figure. So that's what a 1-degree model looks like in terms of the surface current speed. I challenge you to spot the Gulf Stream in those kind of models, but that's you know, that's where we are. So we get to 25 kilometers, you can at least see where the Gulf Stream is. The separation is still wrong, but at least there's something there that looks a bit like a jet and that looks a little bit like a Gulf Stream. So that was kind of what we did for HIRIS-MIP, and then kind of looking forwards towards the next version of HIRIS-MIP and this ERIE project, you know, maybe to try and get down to Eddie Rich kind of scales, so 10 kilometer in the ocean. And I'll say in a minute, it's important to do the atmosphere in a similar way. And this is what NextGems, so Deanne talked a little bit about this yesterday in her poster. So NextGems are running at 2.5 kilometer coupled atmosphere ocean. They're shorter, so it's kind of year to a few decades. They're going to be running for the next few years, but that's where we're getting to at the moment. So we could show that at these 25-kilometer models, we can make a big impact on some of the biases that have been forever in climate models, particularly that kind of cold spot in the Northern Atlantic for the Gulf Stream. And then Eduardo's paper, which you hopefully saw yesterday, looking at the impact of doing the Gulf Stream separation in a different way and what impacts that has in the future. And it is in this one model, at 2050, it projects a 20% increase in mean winter rainfall over Northern Europe, which was outside of all of the other ensembles, be it the CMIP6 ensemble, the rest of the high-risk MIP ensemble, the UK climate projections ensemble. So this is a big climate risk coming from the fact that the Gulf Stream is not represented properly in terms of separation in any CMIP6 model at all. But just doing it differently kind of highlights a risk for Europe. So it is important that we kind of consider some of these biases that are inherent in all of these models. And then I won't say much about this, but Chris, again, showed his poster yesterday. I think Jamie talked about this as well. So the predictability, if you fix the bias in the Gulf Stream region in the ECMWF model. And then this is some work that Sophia Morton did, so looking at the importance of doing the atmosphere resolution as well. So if you look at the SST flux feedback, so if you have an SST anomaly, there tends to be a flux feedback in the atmosphere to damp the anomaly. But if you get the kind of way the model works, you remap the ocean SST onto the atmosphere grid, and then if you then calculate the fluxes, then you'll calculate the flux feedback. But if you get an imbalance between the atmosphere resolution and the ocean resolution, what that feedback should be and what the model actually does can be wildly different. So the feedback won't be right. So you need to take care of what your atmosphere resolution is as well as what your ocean resolution is. So NextGems, so I say, Deanne talked a little bit about this. So this is 2 models in a project that's ongoing to kind of get down to 2.5 to 5 kilometer in the atmosphere and ocean and run for kind of several decades. Deanne showed some work that they're ongoing to look at the coupling strength, and then to kind of delve a bit more into the ocean, where you can obviously begin to look into the sub-mesoscale as well as the mesoscale ocean. So this is kind of where we're going. This is going to be the data that we're going to be able to use in the near future. And then ERIE project, so this will start early next year. So the key science question here is, what is the role of the ocean mesoscale in climate? So we want to run these eddy-rich ocean models and look at what the impact is on the simulated climate and the projections. We want to do similar atmosphere and ocean, so we want to get to about 10 kilometer in the atmosphere as well as the ocean, run multi-centennial simulations. Kind of one question, which I'll come back to in a minute, is what experimental design. So there'll be a long simulation, but also what shorter simulations could we add into the high-risk MIP experimental design? We talked about case studies a bit yesterday. Are there things where we could motivate that high-risk MIP community, that 15, 20 groups easily that could run, if we had a month or a short simulation, we could run it at any kind of resolutions down to pretty much kilometer scale globally. What could we learn if we kind of had the right configuration of a case study? And what kind of developments do we need? So I think these kind of models, they're incredibly expensive to run, but also to store the data is crazy. So what kind of more automated diagnostics, what things should we be doing as the model runs, eddy tracking, cyclone tracking, what flux calculations, what other things should we be storing and doing as the model runs? Okay. So I think there's some common themes in terms of the experiments. What experiments should we use? What should we do? Diagnostics, kind of choices. But I think one thing that I was going to come to, which kind of fed to a bit of what we were discussing a minute ago, is signal to noise. So the kind of seasonal prediction community are immensely interested in signal to noise. So what basically this is for winter NAO, if you run enough ensemble members of the seasonal forecast, you get the black line, so you get an increase in skill as you get more and more members.
But if you do the correlation of a member with itself, the skill is ridiculously small. So basically, there is skill, predictable skill in the real world, but the models have a tiny, tiny part of that skill. So what is it the missing? What is it the signal to noise that we're missing in the models? Is it resolution? Is it physics, the processes, air interactions? Is it the Gulf Stream within the North Atlantic that's causing that lack of signal to noise? That's kind of an open question, but I think if you could kind of give indications that you were going to crack that problem, that that would excite the seasonal forecasters very, very much. Okay.
Okay. Thanks. Thank you, Malcolm. Next up, we have Hyodae. Yeah, we're going to hold off for questions until all three have given their talks.
Thank you. So this is going to be very short. I was asked to provide some sort of summary for the workshop we had last year, summer, supposed to be in Hokkaido in Japan, but it had to be virtual. But that was hosted by a colleague in Japan who's involved in Hotspot 2 project. So I don't have any slide that has description of Hotspot. I suppose Meghan, maybe you might be talk a little bit. Okay, so yeah, Hotspot is the kind of project that a nationwide project in Japan that supports really initiate this air interaction study at major scale in Croatia and Gulf Stream. And they had extensive modeling of initiative and as well as in-situ observation along the Croatia. And that actually sparked a lot of initial progress in if you think about it, like 10 years ago when we just started looking at this air interaction problem. I think there was a definitely great contribution from Japanese Hotspot project on this subject that we discussed today. But then this is Hotspot 2 is kind of continuation of the project. They, if I understand correctly, I think they have a little bit more broader scope now, including marginal seas around East Asia, which are subject to very strong climate change impact, like in terms of seas of temperature warming. So they have a very strong emphasis on the marginal sea observation and air interactions. But nevertheless, they have a still very great focus on crucial air interaction and then downstream weather predictability. So this is was actually a very successful virtual workshop, 126 participants from all over the world. So Shushiro Minobe was the organizer of the workshop, and I was just part of the science committee. But most of the work done by Shushiro and Masami. Masami is the lead PI of the Hotspot 2 project. So this is a very big project. And of course, we have a range of participants from meteorology, oceanography, early career, and students as well from all over the world. So according to Shushiro, this online setting really helped, especially during the pandemic, to increase engagement from the international community. And he was very surprised to see very strong response from synaptic meteorology community, so dynamic meteorology community in this subject area where we talk about atmospheric front and synaptic system in the atmosphere. So we really help us broaden the perspective that we are looking, again, always from looking up from ocean to atmosphere, but there's always perspective about looking down from the storm to ocean. So this was a very good forum to have a very good discussion about how we approach this problem, like discussion we are having now, right, in this workshop. So few notable items. We had a lot of breakout discussion like we do in the CLIVA meeting. Was logistically a little challenging, of course, during this pandemic, during the virtual meeting, but it worked out very well. So I think we had a very reasonable level of social event through this Gather app, which was I thought was very fun to use. And I think Shushiro is still working on the report, so it will be released in some sort of publication But I think some key point here is the high resolution large ensemble in terms of modeling, like Malcolm suggests, high resolution simulation with a large ensemble are the key. And of course, these are the challenging aspects, especially when you have a high resolution ocean and high risk atmosphere. Normally you run one realization, long enough time, but still one realization. So idea is, again, if you're interested in how the rainfall variability will change in like decades, 2 decades later, we need a multiple realization. I think there was a kind of key point that was suggested by numerous participants. Signal-to-noise paradox, the Malcolm discussed this. This was, again, show up many times during the meeting, has to be examined, and then the role of ocean, air injection, has to be also better understood because traditionally we think of sea ice, land, soil moisture, stratospheric aerosol, things like that, some sort of provide low sort of memory to the system, right? But ocean has not been really discussed, especially in context of major scale ocean processes. As Malcolm said, this signal-to-noise paradox implies the models strongly underestimate its own predictable component of the climate system. And the idea is that this western boundary current induced air interaction might be one of the potential source of this underestimation, which implies that we need to be working on this climate scale sensitivity to this major scale air interaction problem. We talked about the extreme events a lot. So a bomb cyclone came up many, many times because these are the very tangible example, right? So how the western boundary could influence bomb cyclone through, again, this diabatic generation of potential energy or ocean front interaction. Understanding mechanism is very different between Kuroshio and Gulf Stream and Agulhas Current and Southern Ocean because storm behaviors are different. Baroclinic waveguide in the atmosphere are different. So, and seasonality or subseasonal variability of the atmospheric jet streams are different too. So understanding this mechanism is very important. Most of the work has been done Kuroshio and Gulf Stream, not so much in Southern Ocean. So there has been some knowledge gap in terms of understanding this process in the different ocean boundary current regions. Increased observation capability is crucial. I think Meghan talked to us about the boundary air flux measurement during the meeting, but I think there was a suggestion about the increased autonomous observations along the western boundary current are important and has been increasing. So, thank you.
Okay.
One last thing.
One last thing.
One more minute. Larry and I are leading U.S. Collaborative Working Group again on the major scale air interaction side, and we have a number of working group members in this workshop as well. And we are organizing a workshop. I forgot to put a slide here. I apologize. We are organizing a workshop next spring in March, April-ish timeframe in Portland on this topic, not just on Gulf Stream, but more on the whole western boundary current region and also major scale eddy. This is kind of extension of the workshop that we had a few years ago in Portland, Oregon, after Ocean Sciences meeting was really well received, and we want to continue the momentum in the community. So it will be supported by U.S. Collaborative and hosted by this working group. So.
Wonderful. Thank you. Okay, and next we'll have Larry. About 10 minutes, okay?
I thought I had 30. So thank you, Hyodae, for the introduction into our air-sea interaction working group. So Hyodae and I are co-chairs of a U.S. CLIVAR-sponsored working group on air-sea interactions, and it's focused on mesoscale and sub-mesoscale air-sea interactions. So it's really relevant. This workshop is actually very relevant to the activities of our working group and vice versa. And I'm just going to real quick, in just a few minutes, just give a kind of brief overview of what our working group is, maybe how it can inform this process, and and whatever. So there are several members, as Hyodae said, that are actually present in this room and online for the U.S. members, and then we have 6 contributing international members as well. And one of the nice things about this working group is we're bringing together observationalists, modelers, and not just in the atmosphere and ocean, but also in aspects of biogeochemistry of the ocean, and also climate experts as well. So it's very interdisciplinary groups. We're really trying to capture, as much of the, important interactions as possible with it. And so basically our working group, the main goal of the working group was just to formulate and coordinate both observational and modeling efforts to assess how oceanic mesoscale and frontal scale air sea coupled processes affects Earth's climate. And so this can be anything from, the storm track processes, but also western boundary currents and things like that. And, we kind of had a kind of a big overview that of, try to do kind of global air sea interactions. But as our working group activities have progressed, we focused a little bit more on mid-latitudes rather than either the tropics or high latitudes as well. And so one of the goals of the working group was to produce synthesis papers. So there have been several in the last 10 to 15 years, for instance, the Justin Small paper, Young Okwan, et cetera, that kind of did a really nice job of bringing together a lot of experts and showing kind of what the state of the art is and then what are the open science questions. And so it's been a few years since a paper has been done like that, and we're now actually working on one now. We've submitted one, and I'll talk about it in a minute. And, we really focused on things like the large-scale atmospheric circulation, Earth's hydrological cycle, so how these air sea interaction processes are, in fact, are affecting the spatial distribution of precipitation, which is very important for, societal benefits. And then looking at, how these air sea interaction processes are affecting both the large-scale ocean circulation and also the kind of the feedbacks onto the local mesoscale circulation as well. And looking at biogeochemical cycles, et cetera, and how these air sea interaction processes are affecting those. And one really goal that, and this is kind of a common theme in when you bring kind of observations and modelers together, is trying to find like kind of basic diagnostic metrics that can really capture the air sea coupling processes in kind of a fairly simple way that you can apply to both models and observations that are robust, and that really tell you something about, for instance, how models are modeling or simulating air sea interaction processes, and how, so it gives them something to kind of aim for, because it's a very intractable problem otherwise. And so another thing was to identify consensus and uncertainties and directions forward in both observational and modeling efforts. And so this workshop is actually really, relevant to this because it focuses on kind of one region, the Gulf Stream. So, for instance, Hyodae was saying that there's lots of differences between the different western boundary currents. So the Kuroshio, has its own kind of unique aspects, the air sea coupling problem, and then the Southern Ocean does as well. So the Gulf Stream is kind of a really nice area that's been, fairly well studied, but there's still open questions. And so we can kind of focus on one region rather than trying to do, a global scale. And, when we started this working group, we started about 2 years ago, and we had these great ideas to guide in situ and satellite observations for optimum sampling of air sea coupling processes. And this would really be guided by, the needs of, simulation, climate simulations, and weather prediction models, but also in, the kind of observations that we have available, either in situ or satellite, and what's coming on. And yeah. So the working group, basically our working group kind of, the U.S. CLIVAR, stepping back a little bit, the U.S. CLIVAR has all these research challenges to try to make advancements for how the science is impacting society. And so there are couple different things, and basically our working group basically maps onto the majority of the U.S. CLIVAR core challenges, and that includes things like climate change, coastal oceanography, et cetera. And then there are also a couple other ones that are really relevant too that we've spent some time on, and this is like the hydrological cycle, marine heat waves, and ocean ecology. And so our recent working group activities, so we're now into kind of the year, end of year 2 or beginning of year 3 of it. And so we've submitted a review paper to Journal of Climate, and we're going through a review process now, so hopefully we'll have that soon. We're spending a lot of time on these beautiful schematics to try to synthesize, the relevant air-sea coupling processes and how they affect things like the jet stream, rainfall distribution, boundary layer structure, ocean processes, and things like that. So it's kind of an up-to-date synthesis of what we've kind of decided. We also have these research seminars every month or two, and we'll be doing this at least for the next year. So if anyone is interested in, and we do this virtually, so if anyone's interested in giving and showing their work to our research group, it's an informal setting, and we'd really love to have you, to hear from all of you. So please contact either myself or Hyodae, and we'll do that. We're also, we've assisted planning of the Gulf Stream workshop. So, check that box. And, but we're also hosting a session at the 2022 AGU Fall Meeting in Chicago. So be on the lookout for that. The session title will be something along the lines of, mesoscale and frontal scale air-sea interaction and its impacts on Earth climate. And as Hyodae noted, we are planning a community workshop, and it's, we haven't started formal planning yet, but the idea is to have a workshop in Portland, Oregon, sometime in the winter or spring of 2023. And so this will be kind of like a capstone for our working group to bring together, and hopefully we'll have a white paper or possibly a second paper coming out of that as well. So we'd love to have all you have that. I just had an example of some of the recent science seminars that we've had that have looked, there's some people in this room that have given them, and I have an updated list in a little bit, but we've had others. So this kind of is the kind of science that we're, that we're talking about in those. And so I just listed some key synthesis points of our review paper and the lessons learned. And so these are all kind of common themes that we're actually talking quite a bit about, focused on the Gulf Stream, but how air-sea coupling, impacts the climate system, the parts of the climate system, and then the importance of sustained global measurements of the oceanic mesoscale. So, we're working kind of more on a global scale, but this can easily be modified to focus more on the Gulf Stream. It came out in the review paper that we really need improved surface fluxes of any kind, heat, momentum, and gas. And the oceanic submesoscale is now being recognized as being really important for Earth's climate and for various things. So it's not just the mesoscale now. So now going down to scales that are, touching, down to about 10 kilometers or so. And then, just beating on this point again is the diagnostics for comparing air-sea coupling between models, observations are really critical for moving forward in our plan. So I think that's everything I have. Thank you.
All right, thanks a lot, Larry. And how about we just save thoughts for questions or ideas from those 3 presentations for later discussion. And in the interest of time, we're going to move on to our next invited talk from Meghan Cronin.
And how do I move things forward?
You can use the mouse or click these arrows here.
All right. All right, thanks so much for having me. And this was a fun presentation to put together. Some of it is oldies and goodies from my thesis, my Gulf Stream work on the Gulf Stream, as well as a lot of stuff that I actually didn't know before last week. And so I really do have to thank all these people on the list here who contributed information and slides, and an apology too. Some of the things that they showed me, I didn't actually get into the slide deck, but I hope to just touch on them. And if not, then apologies. Okay. So this is what I think we should be targeting. I think that we should have a North Atlantic hotspot experiment looking at the Gulf Stream influence on these cyclone bombs and the tropical, extratropical transitions. They just have so much impact on our lives. And, you know, there's tracking $16 billion impact damage from Hurricane Irene. If we can, you know, as the sea level rises, I think we're going to become ever more vulnerable. And so if we can get more predictability, more understanding, I think it will pay off. And so, you know, as we think about why we're doing our work, I think these are the kinds of things that really can benefit everyone. And really, the Gulf Stream is fueling a lot of this moisture that is impacting the United States here and also worldwide, and Europe and other places. So how do we do that? Looking at the array of platforms, I just want to kind of get vocabulary straight here. You have crewed platforms, and that would be like an aircraft and ships. And then there's autonomous platforms, which are like moorings, barges, floats, and drifters. And then uncrewed systems are like those autonomous platforms, but they have somebody who is remotely controlling them. And that would include like gliders or unmanned or uncrewed airborne systems, uncrewed surface vehicles. And I think that as we go forward, we're going to have to step away from, or if you want to really have expansive and sustained observations, we cannot rely upon the crewed platforms for research purposes. We can use them for, you know, like a ferry or commercial ships where we might be able to put on sensors on them. But it is, I think as a primary platform, it's a very expensive solution. And really, as we, you know, go into, you know, more fossil-free living and oceanography, we really need to be thinking about how we do oceanography without, you know, the carbon footprint of our oceanographic research. So with that, the next thing that we need to talk about is what kinds of observations are needed. And so I see there's like 4 different kinds of observations. One is for ocean and atmosphere state estimates, and so that's like mapping. And that might be assimilations into a model, or that then creates like a weather map, or you know, a gridded field of sea surface temperature, or you know, whatever field it is, it becomes a gridded field. You can also do that just straight up without the model, with, you know, optimal interpolation. But the main thing is that you want to have spatially coherent observations so that you have overlapping bullseyes of information for that purpose. The other type of observation would be for validation of models and satellite products. And for that, you want to do intercomparisons. And you really want to have those observations in different regimes. So like if you're doing a time series, it gets like day and night, winter and summer, storms, snowstorms. There's some kind of, you know, you're looking at different regimes. So it's good in here, this regime, not so good. The other type of observation is for understanding and for process studies. And for that, I think what you really want, the analysis you want to do are like governing equations. You want to have, and for that, oftentimes it's like derivatives of covariance terms. And so for that, you have to have both the mapping to get the derivatives and the time series to get the covariance, and for multiple variables. And then finally, once you figure out what the metric is that you want to evaluate, then you can come up for an indicator. Then you can come up with what is the minimum number of observations needed to evaluate that. Okay, so putting that together now, so the first, let's see, the first thing I'm going to talk about is the mapping type. And I'm going to, I mean, there's many different examples of mapping, but for here, I'm going to highlight mapping for hurricanes, because this is where we have a lot of atmospheric boundary layer mapping assets. We have drones, we have aircraft. Aircraft is probably the classic example where you do a dropson from the aircraft. But, you know, newer technologies would include remote sensing from the aircraft, and then there's the uncrewed types of sampling with sail drones and gliders. There's floats and drifters. Okay, so here's an example from the Atlantic sail drone hurricane group. This is a courtesy of Xidong Zheng. And so they had sail drones and gliders working together to observe the hurricane. And so this shows hurricane path and how they were able to actually coordinate both of these to target to be able to map and to get the observations of those passing hurricanes. So the lessons learned from there is that they could do it, that the sail drones could survive, and that they actually could do the coordinated work. And, you know, and that wasn't actually a given. These type of pilot studies are really important. I think before we start putting out all of these different types of new measurements, you know, you have to start doing them in kind of tested out demonstration projects. Okay, so now an example of validation, and this is from courtesy of Joe Sion from the NEOTAC project. And here he has a small unmanned aircraft system that is deployed from an aircraft. And so the problem with these airborne systems is that if they're deployed from land, then you have to have visual sight of them. And so that doesn't work for open ocean. And so then you have to deploy it from an aircraft or a ship. And so that's new technology. And this figure shows how they're doing it from an aircraft. But the aircraft still has to stay within 5 kilometers or so. At least that's at this stage how it is. And it's not recovered. So some of the lessons from that was that, you know, you can't diagnose some of the problems if it doesn't work. But having that drone, be able to deploy that drone from an aircraft kind of expands the whole sampling range and the atmospheric boundary layer sampling capabilities of that aircraft. And so in here, the validation is looking at the model, the WRF model versus the observations through the different heights. And in this case, you know, you're seeing it's bad in the, it was too dry and too cool and dry in the boundary, they're saying. Anyway, work needed, according to this paper, is that they want to get enhanced payload, augmented battery life, increased transmission range, and permitting so that aircraft might not be required to loiter so much nearby. Okay. Okay, now for an example of a process study. And here we go back to a classic example, which would be SYNOP, which was what I did my thesis on back in the olden days of 1986 to 88, I think this was. Anyway, so here, this is, I'm going to be showing you observations from the central array, and it was just an array of these tall subsurface moorings, and they just had 4 current meters on them. And at 400, 700, 1,000, and then down at the bottom at 3,500 with a temperature and a current meter. And then there was a nearby bottom inverted echo sounder with a pressure sensor and a current meter. So pretty simple, really. Some of these had ADCPs on it. I'm not going to talk about that. With that, we were able to, the first step was to get the temperature and the velocities onto level surfaces, and then we mapped them, those like 13 points, to come up with a regular grid using the optimal interpolation. But then, you know, it's like weather maps. We were able to then, I was able to do energy conversions, do the baroclinic, and look at the conversion of mean energy to eddy energy. And you can see in the bottom here that every time there was a big meander growth that you could see in the, let's see. Okay, just to get oriented, these panels here show the 700 meter, which is the middle of the thermocline, temperature, and you can see these big meanders in all of these different cases. And then the little dashed lines are the bottom pressure. And so you're seeing a deep cyclone beneath and a little bit downstream of the upper level trough. And that is the sweet spot for baroclinic instability. And when that happens, then you get water spilling across the front, and you get a big heat flux, or a meridional heat flux. And as shown in the bottom panel, each of these big trough events gives you a cross-front meridional heat flux that then transfers energy from the mean potential energy to the eddy energy. And, okay, and that then spins up the deep cyclone beneath the upper level trough and builds up that big trough into a whole water column vortex. Okay. And we were able to then, with those mapped data from just those simple temperature and current meter moorings, we were able to then map that to evaluate the omega equation and look at the vertical motion. And you could see that you have rising motion upstream of the, or downwelling upstream of the trough, and rising motion downstream of the trough here, right? And in fact, this is the same thing that Amy Bauer was seeing with the Raphos floats that would slide down the thermocline and then slide up them as they're going into the crest of the meander. And so all of this is adiabatic motion. There's no, all the floats here are all staying on the same temperature surface, but they're rising and deepening depending on as the water flows into this these meanders that are growing. And so I think where we go now is looking at how this big vertical motion within the thermocline below the mixed layer affects the mixed layer depth and then affects the sea surface temperatures and the air-sea interactions, and ultimately how this big source of heat affects the atmosphere. So at the Hotspot experiment is, that name is coming from the Kuroshio and the Pacific side, and historically the group that was doing the SynOp, and I have to do a shout out to John Bain, was part of that group. But after a lot of the people did the Gulf Stream, then they wanted to go to the North Pacific and look at the Kuroshio. And so there was this KESS experiment. And with that, there, you know, a lot of the questions were similar to SynOp of what are the dynamics of the Kuroshio western boundary current, and how do they relate to the recirculation jars. But they wanted to have the relationship to the atmosphere, and so then they brought in me for the surface mooring, and then what came out of KESS followed tests was the Japanese hotspot, which is the land, ocean, atmosphere. And so what we have here in the North Atlantic is a lot of this marginal sea sampling through the offshore wind energy assets that Jim talked about yesterday. And we also have potentially have ferries that this oleander that crosses from New Jersey to Bermuda. That could be a platform for doing some atmospheric profiling as well as oceanic profiling. And so this is kind of the process study that I'm envisioning, or what we might be able to do here. I think instead of having moorings, while I love moorings, we could do gliders and then do some kind of mapping with the gliders and sail drone pairs within the jet, and you might have to continually seed that and be crossing it and continually crossing it, and then I think you could have your offshore wind energy assets to give you your land, sea, front, and that's impact on the atmosphere. We could have some enhanced weather buoys. There's several weather buoys out there, and there's no reason why we can't work with the Weather Service to make those be more useful and have sensors that we want on it, and used for research as well. I do recommend having a time series station on the warm side of the jet, and so if you then had a weather buoy on the cold side and an ocean sites buoy on the warm side, there's a lot of cross-frontal study or analyses that can be done, similar to what we do with the Kuroshio between the J-Kyo buoy and the Kyo buoy, like looking at the effect of the mixed layer depth on the heat capacity, the effective heat capacity, and how that might affect frontogenesis. You can also then, attach these sensors like Seth Zippel has for looking at the turbulent kinetic energy within the mixed layer depth. What else? Pioneer Array, great site for looking at the inlet, and yeah, cool stuff. Okay, and then just a final points here about OASIS that I'm co-leading. It's a UN Decade of Ocean Sciences for Sustainable Development program, and so really it's a way, it's such a high level organization. I mean, this is where we want to do the very same things that the CLIVAR working group is doing, right? So, but the difference is that it's a higher plane, and it has, we're working to build the community and bring in, to have the, people from the small island developing states, from the global South, early career scientists, industry, all the stakeholders really participate within this whole scientific enterprise. And so I think that OASIS and CLIVAR really can work together, like we can tag team on things, and we can like build community that then could participate in these CLIVAR working groups and you know, the focus groups, and vice versa. Also, as being kind of a super high level, we can, as a community, really speak and work together to do these big asks, like, you know, call for new satellites and for a whole network, a global network of uncrewed surface vehicles for the global ocean observing system. And, you know, big asks on improving models and understanding. So OASIS, you can get involved because we have 5 different theme teams. Observing network design, capacity and partnership strengthening, and an actions theme team, best practices, and a fair data. So you just go to the website, airseaobs.org. In the upper right, there's a Get Involved button. And anyway, very good. That's it.
Okay, thank you, Megan. We have time for one question. Okay.
Hey, Megan. Evan Jones here for those online. Thank you for the talk. I was curious for the Hotspot experiment that you're proposing for the deployment of like the sail drones and the drones, if you envision that as being more of like a regular deployment regardless of whether or not there's like a, you know, forecasted bomb cyclone or like a TC to move through, or if you think that would be better suited to be based on those like discrete events that are forecast to happen.
Yeah, it's a super good question, because as it is right now, we only get those intensive observations when there's like an event happening. Okay, send them out, go map that hurricane, and it's just right in that along the track. And I think really to do the understanding, I think, and to understand like the interactions between the jet stream and this developing storm and the Gulf Stream, you have to have that broad sampling and long-term sustained sampling.
Thank you.
Okay, great. Thanks a lot. And now we're going to move to the third set of lightning poster presentations. And just like yesterday, I'm going to let Sam introduce people. That worked out really well yesterday.
That works for me. Thanks, Jimmy. Oh, yeah, we started with virtual yesterday, so let's do that today. So first up, we only have one virtual today, but we have Thomas Sprengler. Is that? Yeah, there we go. Okay, so I'll let him do the talking. Just kidding. Okay.
For the folks online, we're just fixing IT right now. We're just getting sound with the presentation. 1 second.
Thoughts?
Hello, my name is Thomas Spengler, and I'm going to talk to...
Okay, it's not coming through here, though. It's not in the room. Sorry about this, everybody. Just bear with us for a minute. Yeah.
There we go. Okay, go for it.
Hello, my name is Thomas Spengler, and I'm going to talk to you about the influence of sea surface temperature fronts on cyclone development. It's of course well known to this workshop that there's a lot of air-sea heat exchange along the major sea surface temperature fronts, particularly the Gulf Stream. And there's a lot of variability associated with that, and most of the heat has been discussed yesterday is actually associated with sub-weekly timescales. So the question then arises, how do these synoptic or mesoscale atmospheric features like cyclones interact with these sea surface temperature fronts? And to assess that, we used the error interim reanalysis data and detected the SST front, and we also detect and tracked cyclones. And then we could basically categorize the cyclones with respect to their propagation, if they're south of the SST front, cross the SST front, or north of the SST front. And then we can look at the intensification and found that the cyclones crossing from the warm to the cold side of the SST front are actually intensifying most. Similarly at the Kuroshio. Now the question then of course arises, is there cause or effect? So maybe the cyclone is just becoming most intense at the front because it couldn't intensify further because it moves to the cold side. So what we then did is we did idealized simulations with WHOI, where we described the jet stream and a lot of different sea surface temperature profiles that we see here. And then interestingly, what we found is that the cyclone development didn't really care about the SST front, the strength of the SST front or the position. The only thing it cared about was the SST about 1,000 kilometers downstream. And that has to do with what is actually feeding the cyclone. And what's feeding the cyclones, and the red arrow here is basically the warm, moist air that's being sucked into the cyclone, which is of course downstream of the cyclone. So it's an indirect effect from the latent heat fluxes downstream. Now, of course, we know that the SST front has an effect climatologically. So then the question was, if you look at these simulations where you smooth the SST front, what causes the difference in the climatology? And then we did the same thing. We tracked the cyclones across this region. And what we found was that the climatological differences are actually not really attributable to the cyclones when they're there, but it's actually to times when there was not much synoptic activity, or as was mentioned also yesterday, maybe there's mainly colder outbreaks, so the cyclones are actually away from the SST front. So in general, we find this indirect effect of the SST front on cyclone development, and the climatological differences are there when the cyclones are actually not present. And what I didn't show, but is on my poster, I'm happy to talk to you about, is that diabatic frontogenesis along the SST fronts in the atmosphere is mainly when there's no atmospheric fronts present. With that, I hope you find my poster interesting. Thank you for your attention.
Next up, we have Robert Todd.
All right, hi everybody. I'm Robert Todd, commuting all the way up from the 3rd floor of this building in the Physical Oceanography Department. Megan's talk was actually a nice lead up to what I wanted to show you briefly, was what we've been doing for the last 7 years with gliders, routinely observing the Gulf Stream along the U.S. East Coast. So the movie there really pretty much tells the story. It actually starts in 2004 with work that Breck Owens did with some early crossings of the Gulf Stream out to Bermuda. And you'll see a lengthy gap until 2015 when we started a pilot program working all the way from Miami to Woods Hole, crisscrossing the Gulf Stream with gliders. The key thing about gliders, they're slow. They move about half a knot through the water. The Gulf Stream is fast, depth averaged of well in excess of 2 knots most of the time. So gliders are advected downstream, but we steer them across. So it's just like getting out of a rip current or getting across a river. You go across the flow, you don't try to fight it. You see these zigzag patterns as the gliders are advected downstream. So in the past, or since 2000, well, in total, we've now done more than 40 missions, spanning more than 3,000 glider days at sea, over 24,000 profiles, over 300 crossings of the Gulf Stream. All of the crossings since 2015 include temperature, salinity, absolute velocity, because we're flying ADCPs on these gliders. We have chlorophyll. More recently, we've started adding dissolved oxygen. These have all been part of various different programs, the General Gulf Stream Observing Program, PEACH, which you've already heard about. You'll see some concentrated effort for 2 years right off of the northern half of the coast of North Carolina. You see it there. And most recently, there's a glider on its way out now. We're extending downstream towards the New England seamounts as part of an ONR acoustics program. We've used these data for lots of different things. Some of that's summarized on the poster over here on the side. But I think most importantly for everyone to know is all of this data is publicly available, both in near real time. It goes out to the GTS. We did confirm last week that unbeknownst to them, ECMWF is getting this data and incorporating it in their models. And it's also, all the post-process data are available and citable with a handy DOI. They're available in one net CDF, or actually 2 net CDF files, one for PEACH and one for the Gulf Stream. Lots of data. This is the kind of thing you can realistically do with gliders. We deploy a glider every 2 months. We've been doing it for years. It works. There you go.
Thank you, Robert. Next up, we have Zaid from Eastern Carolina.
Hello, everyone. I am Zaid Al-Tabi. I am from East Carolina University. I'm presenting team working on using 15 years radar, ocean surface scanning from radar, HF radars, to study Gulf Stream variability. The goal is develop a method, tool, getting Gulf Stream properties, position, orientation, transport, orientation, and form HF radar radial velocity. And you can see here some background about how HF radar works. For those who doesn't know, it's basically sending electromagnetic signals to the ocean based on Bragg scattering the wave. The electromagnetic signals hit the ocean waves with the wavelength half of HF radars. It's bouncing back. If there is a current, we can see, if there's no current, you can see the Bragg peaks, which is from Bragg ocean waves. It doesn't shift it from the theoretical Bragg frequency. If there's a current, you can see the shift here, and from that shift, we can calculate the radial velocity. And here's some, this is a one-time step from, actually, before going to do that, we have a 3 radar coder, 5 megahertz. It's working on direction finding. Actually, Cape Harris, it's a remarkable place because the Gulf Stream falling under radar footprint. And the way we decided to work is using radial velocity because providing more coverage area. And here you can see this is radial velocity as the Gulf Stream enters the radar footprint with the negative velocities. And then we have here the pore side, which is like when wave propagate perpendicular on radar beam. And then here the Gulf Stream leave the footprint. So the idea is using the radial velocity and to get the Gulf Stream properties and providing long-term time series, which is, and the advantage of HF radars is providing hourly measurement with a spatial resolution 5.8 kilometers because we're using 5 megahertz. It is to give a more advantage to the satellite data as we can capture meanders with the short wavelength and give like more details mapping the surface area. There's a 3, I actually didn't mention that the idea behind developing this method, we have like three major questions try to address it. It's why is the variability of separation of Gulf Stream North Cape Harris, and what's the cause for that? And second, how do the meanders at Cape Harris related to variability in upstreams, and also how is Gulf Stream variability related to downstream changing? We're done? Oh, all right, really quick. So the way to get the Gulf Stream properties is using a radial velocity gradient and radial velocity maximum and minimum. We get the positions, and from the position we can get the edge and jet positions. Connecting these position points, we get the orientation, and the width of the cyclone shear zone is from the distance between the edge and jet. And here's some example of the time series. Then there's a two mode bearings, and this is like here we have a DCB here. You can see as meanders pass, pushing the Gulf Stream shoreward, crust of the meanders both push Gulf Stream shoreward, and as it's passed, the trough pushing Gulf Streams from their main positions seaward. So this is basically as a beginning. So try like make it mapping all beams and with like long duration HFA data. So this is going to provide for people like working on modeling and validations. Yep. Sorry about that. Take a look.
And next up, we have Catherine Edwards.
Okay, great. Hi, I'm Catherine Edwards from Skidaway Institute of Oceanography, and about 18 months ago, I joined the Atlantic Hurricane Sail Drone team, full of some really fantastic collaborators at AOML and PMEL. I've listed them here, led by Qidong Zhang and Greg Fultz, who sort of took the role of lead pilot of the sail drones during our operations. So we had 5 sail drones deployed during the Atlantic hurricane season. You can see on the upper right 5 areas that we chose to concentrate our efforts. These are based on essentially the integrated tropical cyclone heat potential, so fuel that might be available for the hurricanes, as well as the incidence of past storms. You can see that on the upper right. Two of the gliders were concentrated in the Caribbean, one north and one south of Puerto Rico. 2 were in the Gulf Stream, one on the inshore side, where I operate a number of gliders on the inshore side of the Gulf Stream and on the shelf. And then in the Sargasso Sea, and then a 5th glider that was sort of served as a storm chaser glider, sail drone. This sail drone essentially served as a storm chaser, and this is the one that clipped Hurricane Sam sailing through the northeast eye wall of the storm and into the eye. The background from the previous slide is one of the snapshots of the video that come back from the platforms. This was originally going to be a video. It's probably for the best because it's kind of like a vomit comet to watch. But so we got some really fantastic observations. I'm going to talk about paired observations at these 2 sail drones, 1040 and 1031. There's a fantastic suite of observations on the sail drone. This was a G1 glider on loan from NC State. We got some really great heat flux measurements and then calculations from the data from the sail drone. Thinking about Jim's talk yesterday about the CliMode data, we saw huge latent and sensible heat fluxes. The latent heat flux was up to 600 to 800 watts per square meter. This is during a time when the glider and the sail drone pair were on the shelf in Raleigh Bay as one of the the frontal eddies on the inshore side of the stream was rubbing up onto the shelf, inducing currents of 60 to 80 centimeters a second and 30 to 40 meters of water. So lots of heat on the shelf, and then a cold air outbreak happened on top. So you had all of the ingredients for high latent heat flux, 12 plus degrees C temperature difference, surface to water, wind, and nice low humidity. So that's a teaser of the data. There's lots of stuff in there. But one of my other focuses as part of this project is how can we do this better? I focused a lot on optimizing glider observations using autonomy to use inputs from models and observational streams to choose the optimal waypoints for a short forecast cycle. How can we do this better with paired observations, particularly with sail drones that have a different set of sort of parameters with which to operate? Autonomous sampling in the Gulf Stream isn't so autonomous, so there's a lot of human input, and finding ways to reduce that human input is huge. I'd also love to figure out how to get these robots to collaborate. How can we use the ADCP data from the sail drone in real time to inform how the glider moves, particularly because this is one of 12 decent satellite images over a 4-month period. You're flying blind trying to find features and use the limited forward speed that you have within gliders. So we want to extend some of the glider path planning control that we've built over the years to USVs, and then sort of enable the cross-platform data and information flow to get better data sets. Thank you.
Okay, thank you, Catherine. So that's all of our lightning talks for today. We front-loaded them yesterday to save some room for some extra discussion today. I saw earlier, if I can take over the meeting, there was some discussion going on in the WebEx chat between, just noted a couple of people, Roger, Arnaud, Elizabeth, Ben, and Chris. If anybody would like to chime in into the room, it looked like a fruitful discussion, and I'm sure everybody in here would be happy to be a part of that. So you can unmute yourself and chime in here. I can see you're still in the WebEx room.
I don't know if Chris is on, but I think the comment originally came from him that he was interested in the possibility of confronting the simulations at high resolution that are now becoming available with case study examples in which the ocean drives the atmosphere. And I guess one of the questions there is how to distinguish what a case is where the ocean drives the atmosphere from a case in which the atmosphere drives the ocean on this sort of scale. And Arnaud had a comment as well. So if either of them are on, I'd rather that they make the comments.
Hello everyone. Yeah, I was just thinking about some of what John Bain was saying earlier on, what we know from previous field work, and I was thinking that one big difference compared to those earlier studies is that we have much better modeling capacity, and so I wondered if it was possible to have a near real-time modeling component to those experiments, so we could actually turn things on and off in the models, and to help to disentangle these cause and effects. Yeah, that's really it.
Hello. I think Roger just described what I previously commented, but it isn't necessarily something we're kind of ready to do immediately, but we're always looking for these examples where we can try and justify or motivate the use of supercomputing resources. So these sort of case studies, I think, are very, very timely. We often do case studies of things like tropical cyclones to motivate higher atmospheric resolutions, but I think this is a bit of an unknown in our system at the moment, especially if we think that currently things are not sensitive enough to these sorts of Gulf Stream features.
Yeah, thanks for that. Comments from in the room? Well, something that Malcolm and I were talking about yesterday was how in some studies of the MJO, they used high-resolution GCMs in something like a hindcast of a weather event. And part of this, what we're thinking about with this workshop is actually saying, okay, from the observationalists, what kind of capability are there, and where would we like to have the observations as GCM developers and evaluators if we were to do something like an extended field campaign. So I think as we go into breakouts, that's something we'll want to kind of keep in mind as well. What was that event called? That Yahtzee? Is that the MJO one? I think so. Okay, other comments or ideas?
Oh, I see John's got his hand up online. You want to chime in?
Yes, is my microphone on?
Yep, we can hear you loud and clear.
Good. Just to follow up on a couple comments, Arnaud mentioned that compared to the earlier the big.
Oh, we've lost your audio now.
Oh my gosh.
But we heard that.
Gosh. Let's see. If you can hear me, I just wanted to that in comparison in addition to the improvements in forecast modeling. Between the time of Gale and FASTNX 30 years ago, there's been a tremendous increase in ocean model forecast. And I wanted to speak on behalf of my colleagues at NC State in Raleigh, North Carolina State University, Roy Ng He and his research.
We've lost you again. Okay. I see you're muted now. Yeah, maybe we should move on. Oh yeah, John, if you want to add the rest of your comment to the chat. I think we lost you right around when you were about to speak for your colleagues.
Okay, we got a comment from in the room. Hyodae?
Well, it's a different topic. Is it okay to move on? Or
Yeah.
should we wait for John? So the PBL, the satellite observation perspective was very interesting. I think we focus a lot on deep convective boundary layer, but I guess, in the Gulf Stream or in the U.S. East Coast shelf region especially, in summertime, you get this incredibly stable boundary layer. And PBL modeling is not anywhere close to capture those variability. It's not really, in an air flux perspective, it's not super interesting because it's low flux, but think about some like fog events or some meteorological events that are relevant to coastal, weather and climate. What kind of satellite capability or in situ measurement capability out there to help models, PBL modeling for the stable boundary layer conditions?
Yeah, I think that's really appropriate because I imagine that that's the synoptic conditions that we have right now, like over the last couple of days, relatively stable. Okay, Caroline?
Yeah, and if you read the study report that Zhao's talking about, there's definitely a section in there that mentions this impact about stable boundary layers. And there's a picture of the stable boundary layer on the cold side of the Gulf Stream versus from Cly mode that Jim showed. It's in there because I was like, it's not a lack of wanting to have a higher resolution. It's a lack of technology allowing us to have that higher resolution. So, you know, you just know that there's all kinds of stable boundary layers we're just not going to capture with that. Conversely, if you see how many actual profiles we have of the atmospheric boundary layer over the ocean, open ocean at all, you know, getting something was sort of it's a huge step change, but it definitely, absolutely is not capturing that. And so to what extent it would help us say of the boundary layer development across the Gulf Stream, you know, that providing boundary conditions maybe for the models.
Okay, great. Any last comments from folks online? We're at the 10:30 mark.
Yeah, I think I'll take it back over here. So we're gonna go into break in a minute. All right, let's get started here. Elizabeth, I think you've picked the first spot because you picked the first slide. So you can kick it off for us here.
Ready. Okay, the first virtual world thought a lot about designing a research field program or modeling program, and we had the guiding principle or feeling that the best field programs have narrow scope and are hypothesis driven. They have a goal in mind that's very clear that everyone can rally behind or can clarify. And we noticed that these often are trying to fill a gap or uncertainty identified by the modeling community, and that helps focus things. Example are, say the model says there are 3 possible hypotheses. We need to measure certain processes to support or deny those hypotheses. We liked that model, and so we tried in our discussions to try to clarify where those gaps were in models and or reanalysis. Case studies still seemed valuable for high resolution modeling experiments and improving process understanding, in addition to things that we thought we could solve, the things that we thought we could go after with a long-term observing strategy. So we kind of have both things in mind. And with that, the guiding questions for future work became which fields, processes, or weather climate impacts are not well modeled or are not well represented in reanalysis. And I guess that goes for parameterizations too. And here's our long wish list. This is going to look really familiar to everyone. Surface fluxes, winds, waves, and their gradients near strong currents. Those impact both the ocean and atmosphere. Surface wind convergence, how that works and where the impact goes up and down into the ocean and atmosphere. That's trackable, that supports. And like all of these support our hypothesis, like surface wind convergence is the primary mechanism by which the Gulf Stream influences the free atmosphere. You know, like, so all of these could be said, this is, we think this is happening, or the hypothesis is this is a strong factor, or this is a weak factor, and then you could measure that and say yes or no, that's true. So similar transport in and out of the boundary layer, which can be measured, that's a key pathway for impacting the free troposphere. Are any of these surface-related features or surface-related processes impacted by this ocean submesoscale and mesoscale? If so, how, when, and where, and to what extent? You can measure diabatic heating from precipitation in clouds, how that impacts the upper atmosphere. Then we have a lot of surface and other scale issues like non-wind driven surface exchange physics. So for instance, a lot of parameterizations at the surface are based on wind speed, and that can break down when currents are playing a large role in determining the stress vector, or in high winds when different regimes take over. Non-local influences on the fluxes, such as when the location is downstream of really strong surface gradients and the local parameterization might not be representative. S2S and synoptic timescales are really hard to predict, so that's a target for us, as well as the climate scale impacts of the Gulf Stream, like heat transport and large-scale SST patterns. Submesoscale ocean processes are not well modeled, including the vertical velocities along fronts and other strong features. The impacts of the atmosphere on the ocean, we would like to measure and understand better. And then the parameterizations of all manner. A hypothesis could be formed that if all of these parameterized processes could be better measured and parameterized, maybe the models would be a lot better. Seems like you could go after that in an observational field campaign supporting parameterizations next. And so with that, we talked about observing strategies for these key processes that the modeling community has used successfully before and would like to use. For instance, we would do well to measure what the models produce in terms of the process rates or the exact fields and how they're represented in time or space, and to measure the impacts of the process. So what we think the submesoscale ocean dynamics are doing to the next field. We would want to measure both of those. In terms of trying to measure ocean submesoscale processes, including waves, we thought about networks of long-term repeat surface or subsurface measurements. So a variety of platforms, say, that circle a mooring or are in tandem with each other, or cover a large enough area that they're out there for a long time, they can capture events. For the atmospheric boundary layer and cloud layer hypotheses, you can fly flux-capable drones that have fast sensors. You can fly them through the boundary layer and into the cloud layer. You can also use vertical profilers on aircraft or from ship or towers to solve for variances and fluxes. Similarly, ship and aircraft both have very capable precipitation and cloud radars, including wave radars that are, drawing out swaths of data. You can also retrieve turbulence and latent heating in the atmosphere from those. You could also use ship or aircraft-based sonde deployments, so radio sondes or drop sondes. And those were highlighted as a way to produce really useful composites of a single event or many events and cross-sections of dynamics of interest. You could do that over many events and background states. And you can also use a circle of sondes dropped from a high height to solve for dynamical budget quantities, which could be compared to models. We also stressed the emphasis of using prior successes as learning models. There's many prior field campaigns we discussed a lot. I will put them in the notes for the workshop, and also drawing on the successes of these platforms already usually being in use by the NOAA National Hurricane Center and the NOAA Winter Storms Program. So they're doing flights over the eastern seaboard for storms of interest. And I meant to write down coordination with high resolution or opportunistic satellite products. That was on our radar and I just didn't have time to write it in. The last one was process-oriented model diagnostics that to save while the model is running, or to know that the model should be analyzed with respect to, since that model output is really voluminous. And so if we already could narrow down a few fields to look at, and examples are things like SST wind coupling, or sort of those relationships that we know we want to look at. And we had a recognition that our goals and results and would be time and space scale dependent. That's it from us.
I think I unmuted just in time for you to miss the raucous applause, but.
Thanks.
Okay, next up we have Nathan.
Sorry, I added to it. So this might suffer in comparison to Elizabeth's report out, but someone has to take one for the team. I guess I can click here. Okay, so really, there we go. Okay, so what we did was we took the first 3 bullet points, or the first 3 questions, and we sort of coalesced them into one. For each scale, which are the physical processes that are best and worst captured by observations and models? So we started with the negative part, of course. Atmospheric models have difficulty with rapid intensification, which is tricky to categorize that in terms of scale because it's a large scale phenomenon. that results from the integrated effect of many small-scale physical transfer processes. And I guess you can probably say up and down the line that none of them are really that well described. Otherwise, you know, it would be better described. So the position of the Gulf Stream separation is also not well resolved by models. And, you know, we can debate the degree to which that's true or not. The vertical variation of the atmospheric boundary layer is not well observed, to echo Carol Ann's point. The impact of sub-mesoscale eddies and filaments on ocean surface waves, and then from those on to fluxes, is poorly resolved by both observations and modeling, so that's a twofer. Going further, how much of this poor resolution is the result of application of bulk formulae into situations where they're not well suited? You have, you know, stationary conditions without too many horizontal current or sea surface temperature gradients, and you derive a relationship between wind speed and some transfer coefficient, and then you go into a highly heterogeneous area and you apply it and you don't get what you expect. Whose fault is it? Well, okay, so that's enough negativity, but it does seem like ocean seasonal stratification appears to be well modeled, so that was a check. And then satellite winds via scatterometry, that appeared to be a remote sensing success story. That was my editorial comment, the success story part. But it does seem like because the scatterometer is directly observing, well, it's scattering off of ocean surface waves which are directly responding to wind forcing, it's less of an ad hoc measurement than some other techniques, and that might be one of the reasons why it seems to do so well. Okay, so from that point on, we decided in towards maybe the latter half of the first breakout, but then certainly into the second version, that we wanted to spend the time thinking about what we'd want from an observational and modeling effort. Okay, so there are really hard problems with trade-offs. You know, there are no solutions, just trade-offs. For example, just increasing resolution increases your computing time, data storage costs, et cetera, as we all know. So what scales do we really need? And so it was determined that we probably don't want to say, well, let's get from the planetary scale down to dissipation scales. We need to find what is basically the smallest scale, or I guess really, what is the largest scale that the process-oriented people would be comfortable with? And then we'll just parameterize from there down. Okay. And that is going to help us to find a balance between how much compute time we need, how much storage we need, how many people hours we need in terms of analyzing and that sort of thing. So using ensemble modeling to change a parameter in a region and then explore how much it influences the outcome. So you can imagine perturbing the sea surface temperature or the current or the wind in a certain location, and then what kind of downstream effect does that have, both in, you know, stream terms, Gulf Stream terms, but also in terms of time and, you know, regions that are surrounding the Gulf Stream. So also we would need to determine the required scale that would be needed to model such a parameter, and then use that information to inform observation. So this was framed as an inverse problem, where basically modelers tell observationalists, you should maybe make your observations over in that region because we think it's particularly, you know, determinant of outcomes for near-term forecasting. And then choose the best locations for data assimilation. I stole my own thunder. And then use the modeling to inform the locations where observations make the most impact, right? Okay. So impose parameter changes and gradients and resolution to understand the impacts of making these changes. For example, subseasonal to seasonal variability. And a question, which I think was posed by Carol Ann yesterday, if we knew the Gulf Stream position and dynamics 3 months in advance, how would that help our predictions and understanding? And is that really what we're after? And if so, how would that affect our forecasts of weather over Europe, for example? So I think that's the classic. If we were the dog that caught the UPS truck, what would we do then? If we finally were able to perfectly model the position and dynamics of the Gulf Stream, what would be the impact for the modeling of weather and climate? And maybe by framing it in that way, we can determine, well, is that the thing that we want to chase? Or do we want to chase more fluxes or something of that nature? Okay, so I think we were all in vigorous agreement, and I was actually surprised that we came to the same conclusion independently in our breakouts as we found in the second. We'd like to have continuous monitoring and the ability to send our observation systems out in advance of an event. So possibly a fleet of autonomous vehicles that are sampling in a region, and then when a certain, an extratropical cyclone or some kind of interesting system is developing, we can nudge it as a flexible asset towards the region of interest and make really high resolution intensive measurements in our region of interest before, during, and after the period. Okay. So preconditioning for atmospheric modeling is important, and that is basically the follow-on from what I just said. Let's say that we know the system is developing over a region. Well, we want to have the autonomous vehicle there beforehand to measure the initial conditions, and then look at the run-up as the intensification or whatever begins. So if we ask the modelers what field data would change their lives, it's a bit dramatic, but I think it fits, what would they want? Let the observational folks decide if that's feasible. So this is that famous handshaking, that back and forth that modelers and observationalists do. So sometimes the tropical cyclogenesis and propagation is slow, and everyone laughed out loud at the May 2020 Outer Banks storm that famously blew onshore for 4 days. So in these cases, oceanographers with soccer kids are not available during game time for rescheduling, and Mike is at home in the Outer Banks. This is radar Mike. Because the weather is lousy, I kept that in. I thought it was a good comment. So would a permanent shift in the jet stream shift the Gulf Stream separation point? That's an open question to be resolved. And the people in the room and others who actually know what they're talking about, not me, are not convinced that it would change the separation point. I think there was a consensus, or there was a sentiment at least, that we need to get our observational capabilities of sufficient spatiotemporal resolution to sort of see eye to eye with observations that are becoming increasingly higher resolution. A good way to do that is to use radar and measurement systems that give you a time series of current or some other parameter over some region and resolved in space and time. And so hourly, for example, high frequency radar could provide long-term observations to measure Gulf Stream variability. And we talked about this pipe dream of putting HF radars on barges scattered throughout regions of interest to give us floating high resolution wave and current measurement platforms. HF radar or X-band radar, some sort of electromagnetic wave transmitting system that gives us what we want. We can figure out the details later. And we want to cover different areas. So the cold and the warm side of the Gulf Stream, because we know that coupling is very different on either side. And we want to get the boundary layers on either side as well. Obviously, mooring something on the warm side would present a bit of an engineering challenge because it'll probably just break away and move after a couple months. But, I guess we'll have to see where the interest is. That is it for Breakout 1. Thank you.
Catherine or Malcolm or both?
You get 2 for the price of 1. Go ahead.
You were going to lead off.
I thought you were going to do that one. Well, in our first session, we started off with kind of building on Meghan's dream that she talked about in her talk. Thinking about a winter observatory as sort of a framework for what would our observations be. And like one of the previous groups, we also thought about having something like an X-bar being the center of a Lagrangian sort of array, and you could have a fleet of autonomous vehicles traveling and sampling repeat patterns underneath it. So you can move towards multi-scale observations of processes and then continuously feed upstream and let them kind of float on their way downstream. And in this way, you could get some combinations of measurements that would assist with modeling. Obviously, the modeling efforts would be pretty significant and multi-scale, and as much as our tendency is want to capture everything all the time and everywhere, that's just fundamentally not possible. Did you? I can't remember really, honestly.
So just taking the second point, which I think kind of overlaps with what you just said. So we kind of talked a bit about the difficulty of trying to do observations with event-based, so trying to do events, is that it's not just the event, it's the precursors, it's what the kind of background conditions were beforehand, and then how do you kind of get all of those observations as well in order to actually get how the event's going to kind of work. And then so we didn't have any solutions, but kind of that's a problem that if you're going to do it based on events, then how do you encompass all of the things that you need as the background state beforehand?
Yeah, particularly recognizing that any errors you get, as we've discussed in multiple ways, are, they're not necessarily local scale errors. They're in some ways accumulation of that preconditioning and potentially from faraway places. So the scale of the errors can be different from the scale of their sources, and how to determine the difference between, are there errors in the ocean state versus errors in the flux and coupling? Like, how do we figure out which is really the problem in a smart way? Sort of our next kind of bullet point we spent some time on in the first session was connecting event scale observing and modeling to communities of practice. And this is something we keep in mind as people looking for funding. And that's something that we want to demonstrate the importance of our work, not just because it's cool science and we've got really cool toys, which we definitely do, and it definitely is, but also because it's important, and not just to people who live on the East Coast who are directly impacted by storms, winter storms and hurricanes, but also kind of on larger scales through the impact of these kinds of forecasts on ports and navigation. And then also for fisheries impact. There are few people of us scientists who communicate our science well to all of our stakeholders. It's something we're not necessarily trained to do and don't always do well. There are a few of us, Glenn, who do this particularly well, but it's something, if we were to spin up this sort of dream to keep in mind, the other sort of stakeholder or community of practice that we don't want to forget is biogeochemical collaborators, our collaborators even within ourselves. How do we take experiments of either old data sets that we have and share them with others who are interested? How do we build these things around people who are interested in Hurricane Irene or some event? And then similarly with the biogeochemical measurements, these are things that should be built in at the design phase and not treated as an afterthought. So bringing in some of that, expanding that larger community will increase our impact and participation level. One thing in our second session that was really a hot topic, it came up as, what are things from the ocean that may be neglected or important? And it was recognized that we hadn't been talking about salinity very much. We can think about salinity as, in statistical models, it was brought up that statistical models can do really well with just using salinity to predict a lot of important stuff. But it's the integrated measure of evaporation minus precipitation, and it's modified by mixing. So it's two things that are hard to measure and hard to get right with the evaporation precipitation and then the modification of the mixing. So it makes sense that it would be tracked statistically in sort of a simple level. Tracing it back to the processes through the chain of how it got that way is a lot harder.
So just inserting before ERA 6, so one other thing we talked about in the second session was coastal impacts. So talking about, I think there was a big rainstorm on the East Coast a few years ago that dumped a huge amount of fresh water at the coast, and then that drained from Cape Hatteras and potentially had big impacts on the Gulf Stream and the separation. And kind of we were hearing that there's been huge variations in temperature and salinity right at the coast, kind of off New England and elsewhere, affecting fisheries and the like. Now, are those trends or are those variability? That some of the variability has not been seen kind of before, changes of 0.5, 0.6 in salinity and a few degrees in temperature. And these are big differences. How those differences from the coast also go on to affect the Gulf Stream. And, it's very consistent with Eduardo's picture of how the Gulf Stream might change in the future. It might shift northwards and how that would change stuff downstream. So I think that's kind of an interesting thing to think about as well. And then the final thing, it just kind of came up at the end. It's something that I learned when we were putting the ERI proposal together, is that the plan is for ERA 6 to be a coupled reanalysis, not just an atmosphere analysis. And that obviously poses huge new challenges because you're going to get the whole couple system right. You know, you need to get the Gulf Stream in the right position because, as we saw from Chris Roberts' poster and elsewhere, you know, that has big downstream impacts if you don't get the Gulf Stream and the fluxes right. And so I think all of those kind of challenges to put that together are exactly the kind of things that we've been talking about in terms of observing and modeling these processes better. So I think there's potentially some alignment and kind of common issues and things that we can work on together that could, I mean, we talked yesterday about how good or otherwise reanalyses are and how much we should depend on them, but actually maybe we actually play a role in developing and making sure that the reanalyses are good if we're gonna complain about that they're not good enough at the moment. So, okay.
Okay, and then finally we have Roger. Are you there?
I'm here. I am here, and I have 2 or 3 relatively sparse slides. I think it's roughly the total number of characters I'm capable of typing in half an hour. And in addition, the second part of this virtual session was joint with the one that the one from Elizabeth and Justin, and so some topics have been covered already. In any case, we had a pretty broad-ranging discussion. I'm not going to try to repeat all of it here. I'll just pull out a few things. I think eventually, in terms of scenarios, sort of the discussion kind of coalesced around 2 possibilities or 2 focus points. And one is the problem of sort of bomb cyclones and extratropical transitions that where geographically we're sort of focused around the Gulf Stream separation region. The other one is more general cyclogenesis and baroclinic development over the separated Gulf Stream, you know, off into the region south and east of Cape Cod there. So these 2, they have similar timescales. So in both cases, we would be trying to resolve storm event timescales, but also stay out there long enough to capture several events, because the interactions between events and how they affect the ocean heat content and where things come from and are coming from in the atmosphere are important as well. So this leads to maybe something like a month of intensive observations. And I think these 2 possibly have somewhat different spatial scales or extents. So we could go to the next slide there. So for the Gulf Stream separation region and that problem of rapid cyclogenesis there, things like the accurate position of the Gulf Stream front, even though it's confined by the coastal boundary there, the variations of 50 to 100 kilometers in the offshore direction are really critical and change the land-sea, effective land-sea temperature contrast and the flux contrast. So those scales are very important. And some of the problems of interest are, again, to determine the heat content of the upper ocean, including all the small-scale structure, such as filaments and warm rings, and how the heat fluxes play into or are affected by that. And the question of whether the evolution of the ocean state and that upper ocean heat content is going to be important for the forecast on this time scale of weeks to months or so. And for the downstream separated Gulf Stream problem, one of the tensions that seem to arise is it the local SST gradient or the sharpness of that SST gradient across the Gulf Stream that's important? Or is it sort of larger scale structure, the contrast between the SST and the cold air sector and to the northwest and the warm air sector more to the southeast, loosely speaking? And in that region, we also can expect a more complex and wider ranging Gulf Stream and upper ocean structure, as it's not confined by the coastal boundary. And in both cases, what would come out of this seems to be likely case studies. You know, this is not a long-term monitoring sort of thing, and not really, you know, like a new bulk flux parameterization out of these this month of observations. But this could be very interesting if we find that these cases show a strong effect of the ocean, or especially the ocean evolution on the atmosphere. That could be very interesting for evaluating forecast models and understanding their sensitivities to this part of the problem. It's a big job, but if it yields even an incremental increase in forecast skill, that's a valuable thing because those are hard to come by, and we're used to working hard to get those little increments. So one last slide here. I think one thing that maybe we should be thinking about is what measurements. Let's see if you could go to that last slide, Sam. Is it there?
I don't think it's.
You might have to.
I don't think it's there.
On the other place, but if not, the main thing here is just what are the measurements in the free troposphere, if any, that we need, and should we be thinking about aircraft? And is that something? Should we focus only on the boundary there, or do we need that information? Can we get it from the large-scale models? And along with that, there are some previous and planned programs that have included aircraft. Gale, that John Bain, for instance, and Chris Farrell mentioned. Here we go. Okay, Thorpex and the NOAA decks, which was towards the end of Thorpex. And there, in terms of planning, it was mentioned that there is, if I can find the acronym here, the North Atlantic Waveguide Dry Intrusion and Downstream Impact Campaign that's sort of in planning now for something like maybe 2026. And I've just stolen their nice little graphic down in the right-hand side here to indicate that there's a connection here with the area that we're talking about and the processes that we're talking about. So this is possibly a connection that should be explored. So that's all I have. Thank you.
Thanks, Roger. Now we'll move into, I think that's everybody, right? And then we'll. One more. Oh, one more? Chris. Oh, I'm sorry, Chris. Okay, I'll put that up for you. That's what you mean, yeah? How do I page through? Let's make this big here, and then I'll help you out here. And you just go 2 fingers.
Ooh, okay.
Or you could arrow if you're afraid. Yeah.
2 fingers? Yeah, that's not good. I'm not a Mac person.
Finger, yeah, just
this way?
or down.
This way? Or this way? This way. Ooh. Cool. Oh, this is gonna be weird. Okay, so we cool. We covered a lot of the similar points that were already discussed. Hopefully I'll highlight some things that were a little different, or what we spent most of our time on. We kind of went through each of the bullets in succession, so it was a little more. Well, we went through each bullet, but then we would answer bullets from further below in the whatever bullet we were in. Anyway, so for this first one, we never really described the scales of the observations that were important in the model domain, because it was difficult to answer. But that said, some examples would be, say, from satellites and winds, when you're comparing area average systems or area average points in a model to a point measurement in the open ocean, you have some difficulty. So this gives up representation error. So we think of this in terms of matchup with satellites and in situ. So there's always this space-time relationship between models and observations. So one of the examples was when we compare models and observations, we're using typically a point measurement. So we choose the model grid point nearest to that observation. When you want to generalize, you want to apply that over the whole domain. So if you assume the relationship between fluxes and inputs are the same based on point buoys, there are a lot of other things that are not captured by this observational point, obviously. So it's mitigated by a long time series of observations and capture more of the parameter space, or by many grid points so that they're more representative of the space. And from an additional perspective, if you're looking at what the representativeness of this field is in a grid box scale, the spatially average temperature, say, to compute a flux. There was an example we talked about that the ARM people did this over land, did some filtering to get what they think the GCM grid box should have to make their observations. But we need observations to fill the grid box. So to compare these large scale patterns, but the actual magnitudes might not tell you what you want to know. So with this context, we started to think about, okay, what observations or what kind of an observational program would you want to, how would you approach this with this context in mind? And from an atmospheric point of view, using drones that you could, map out a full grid of the state variables that you're interested in, and fluxes of the atmospheric boundary layer. So, and you can map this out rather quickly. And I'll talk more about that a little bit later down below. But also the vertical resolution, this is like the theme that came up throughout the discussion so far, but the vertical resolution in models may not be optimized for air-sea interaction that we're interested in. I don't know how that'll go all the way down there, but for instance, also on the ocean side, CTDs have all kinds of variability and structure, but models will throw this out, or some parts of this out. So when we started looking at question 2, one of the first things we identified were that stable boundary layers in general are not modeled as well as convective boundary layers, just as a general statement. But when we started thinking about different scales in models and what they do well at, there was consensus that the 1/10 of a degree captures most aspects of the mesoscale deep coupling that generates Meander-Sand Kuroshio comparisons, but nothing in the sub-mesoscale is at that scale. So we do pretty well with ocean energy statistics, but this doesn't mean that we're getting the SST correct, because this is only at the thermocline depth. So the question is, how is this variability at the thermocline depth related to any surface frontal expressions? And it was brought up that Baylor-Fox-Kemper has some parameterizations, and they've been included in the MOM at the 1/10 of a degree. So there's some way to incorporate models or incorporate observations into models, maybe through this framework. I think people have talked about how the downstream atmospheric development is important to the extension, but getting the separation off the coast is probably key to seasonal variability. And regional models tended to get this correct, but not in 1 degree climate models. And then we also discussed how ocean vertical mixing is parameterized well in models, is not parameterized well in models, so because the scale is much smaller than the vertical, than the horizontal, and that wave-induced mixing at the surface is very important, or is not parameterized well either. Another thing was that atmospheric models don't get low clouds well, so there's lots of variability between the models, and this is important to the climate response. We also had a short discussion about how internal waves and the associated vertical velocities may be important, and also inertial pumping associated with the passage of cyclones may also be something to think about. This is very rapporteur centric here in the language. So here we were just kind of discussing what we know well, or what we could describe in terms of physical processes for modeling. So we could describe the separation from the coast. In a 1 degree model, we could describe the separation from the coast rather well, the transport through the Florida Strait, the number of warm core, cold core rings, describe SST from and SSH from satellite. The size, this is also what would be important to models. The size of the 18 degree ventilated water area, the jet stream, this large meanders, both in situ and satellite data, the cloud properties from satellite data, and precipitation. And Caroline's a very big proponent of temperature, humidity, and from satellite data. And we also were thinking of coastal currents, which have been mentioned from HF radar throughout. So again, tying back in with this inertial oscillations, can current models capture this inertial spreading of the cold wakes of extratropical transition, as you see in the Curcio Extension Observatory? So, ooh. So what are the, I think many of these has been touched on previously, but what are the important observations that we think we could accomplish or that are important would be definitely direct covariance surface fluxes across submesoscale fronts, doing atmospheric boundary layer flux profile, so doing fluxes at various altitudes through the planetary boundary layer. What's the simultaneous structure of the atmospheric boundary layer across the front, both on the ocean and on the atmosphere? So again, what's the temperature salinity and the currents and the waves at scales that resolve the gradients at the submesoscale front and across the front? What were the surface pressure? What's the surface pressure gradient across the front? And then we had this discussion between how do you want to say, coastal versus open ocean observations. So in the coastal area, you need a lot of observations before the separation. The open ocean maybe provide an easier framework for modeling than it would in the coast. We'd also want, you need a number of realizations. If you're thinking of, say, storms coming through, you need a number of, I'm always a proponent of the more, filling a parameter space, getting more statistics. So we're always confined by how many actual storms are going to come through and as an observational program. We also had a brief discussion about how observations of deep ocean and surface ocean structure, similar to Meghan's or an additional SYNOP2. And Caroline pointed out that coupled OCs would be really helpful in this context. And then finally, so following up on the previous one, this is very similar. What kind of observational campaign would provide process level understanding? So at very small scales, we'd want to look at the coupled boundary layer structure and the evolution across fronts, including moisture and clouds, looking at the wind wave current interaction on both sides of these fronts. The vertical velocity is very important, as everyone's been pointing out, across the whole coupled boundary layer system. We also talked about upwind measurements of things, so upstream in terms of preconditioning the system is important. And again, directly measuring surface fluxes across the fronts, atmospheric boundary layer flux profiles, and similar processes we talked about earlier. But also, if we're looking at storms and how they impact or how they interact with the Gulf Stream, wave breaking is going to be critical, aerosol, sea spray, and bubbles in bubble media exchange in the ocean. And coming back to the point about whether you want to look at a non-shelf location may be easier to evaluate with a model than in a coastal zone. And we also we feel it's very important, even though looking at Lagrangian systems or measurements would be very useful, it's still very important to have long time series for Eulerian observation. And that's where we came up with. So I'll just stop there. Thanks.
Okay, thanks, Chris. I had to figure out how to move this TV. Are you guys taking over?
Well,
I'm being
unless you
formed.
want to lead the discussion.
No, I'm all right.
You can.
I hate
Totally
to
fine.
get
Yeah, so we have time for some discussion. So I want to say one thing that Chris mentioned, that it came up in there, but some of my thinking is I once had a very, very long, I was calm on my side, but my fellow land boundary layer person was not. It was actually quite fun. He had a very strong Australian accent, and we were in a French bistro, and he was getting more and more excised, and every time he said Monin Obakov, I think the people around us got visibly more and more distressed. I don't know if they thought what we were talking about, but he was, I mean, you know, he's at one point he's like shouting, but Monin Obakov. And anyway, it took us a good 30 minutes of discussion before I could understand what his concerns were, and he could understand where we were coming from. And here was the big difference. Because they don't believe, it's not a belief. They are always strongly aware of surface inhomogeneity. Okay? So when we're talking about like the gold standard and we say direct covariance flux measurements, like that's, everything's got to map to that. And if you are on the land side, you go, yep, all right, now we do a basin model and we do all this, and they adjust their direct covariance flux measurements by 20%. Right? So we were having this long conversation, and we realized it really is, because they're like, the inhomogeneity of the surface is so strong that is factored into everything that we do. And so some of the stuff that we were talking about in that thing is that we, I think, as a field, are very often still coming from the feeling that the ocean surface is pretty homogeneous. And we haven't yet adjusted our thinking to saying, we may have to think a little bit differently if we're going down to these scales. So this, the prime example of that is the fluxes, right? And just that, we are making a lot of assumptions about, frozen turbulence and that we can actually, make observations and average for 10 minutes, and that actually gets us something that's kind of the right value, and that the flux parameterizations should work across those kinds of fields. That may not be true, right? It's quite possible that what eventually we may have to do to get this learning better, to actually set up something like a coupled LES simulation, actually doing a U prime, V prime, W prime, T prime, Q prime, right? And instantaneous fluxes, and then looking at those over some time. So it's just one of those things that I think that we were trying to get to in our group, was that we still think a little bit that the surface is very homogeneous, and we're getting down to scales where that's not true. And if we're like in the Gulf Stream and the mesoscale front salinity. So anyway, that was some of it.
And not to be a wet blanket, but our gold standard comes from a Reynolds decomposition that may or may not be valid if you have transient conditions, eddy covariance. So that's
right. That's the point. Right. Yeah.
But once we lose stationarity, what do we have then? How then can we quantify our fluxes? Because obviously the ocean atmosphere is still interacting if the wind speed is changing.
Well, yeah, and that's why it's like getting the actual, U prime, V prime, W, getting some aspect of that and putting that into a system, and then having to rethink about how we're going to do those flux parameterizations. Not with this, we're going to add a little gustiness here, we're going to do a little bit over here, and that's going to kind of take care of it. It may take some real rethinking of that when we go to these scales. So it's something to just be aware of, that we have to, I think we need to think about that in a little bit. It comes up in, like, we talk about it in a few little places, but then I think it really is driving a lot of the things that we're talking about. But Megan, you've got to.
I just wanted to comment on, now it's turned on. I wanted to comment on the summaries, which were really excellent. And I really appreciate that there was a lot of discussion about these different this potential process study or field study. One thing that I've been hearing about a lot of here, I had focused on the bomb cyclones, or yeah, the bomb cyclones. But I think what I'm hearing consensus of is that there's not going to be enough statistics, really. If we just focus on that as a winter storm, then it's going to end up just being a case study that might or might not happen depending on our luck. But if instead the focus is on more generic types of cyclones and winter storm development, that then there can be more statistics, and that will make any kind of a field program more robust. So it seems like that was coming out of some of the discussions, but I see that as, reading the room as kind of an important point. And then the other thing that I'm struck with is that there's been very little discussion about the summertime storms. A lot of discussion about the winter storms, but not the summer storms so much, at least in this synthesis discussions. And I'm wondering whether, in fact, that was intentional, or whether the other groups, what people are thinking on that. And then the final point, is the name, right? It's nice to have a name. And I had been talking about a North Atlantic hotspot, just kind of going off of what the Japanese are doing with the hotspot out of the Pacific. But I do like this synop too, and actually the ocean atmosphere synop, because in fact all of these features are synoptic scales, and their interactions with other scales, both in the ocean and the atmosphere. So those are my comments.
Yeah, thank you. On your first one, if we are missing measurements in a particular environmental condition, can we implement semi-automated adaptive tasking for autonomous vehicles that help us to chase features that we think or we can forecast are going to develop in the next 12, 36 hours or something, and basically force our measurement to be made in a particular location? Maybe that's putting our thumb on the scale a little bit, because we're oversampling a certain part of a storm, for example. But that does seem like, a way that we could sort of fill in our parameter space a bit if we're lacking something above 20 meters per second, for example.
I'm going to go a slightly different direction with that and say, I think there's still a lot that we don't know about the coupled ocean atmosphere boundary layers across the front, in the frontal region. And then we're going to pop storms on top of that and address that problem. That's why I'm sort of a fan of, a combination of different things, but some of them is to just get realizations of the unperturbed system, where we, actually can say, yeah, when there isn't a storm going by, we do have some sense of what the fluxes are across the system and what the boundary layer sort of looks like. And then when you add the storm on top of it, then, then the changes are like this. So, that's kind of a different thing than just waiting until there's a storm and putting out all of your assets sort of ahead of the storm, and then during the storm, and then after the storm. I don't know, but I might be the only one here who thinks there's some value in getting both the background and then the perturbed conditions. So. Turn on. Is the green light on?
This is Robert Todd. Just a practical answer to Nathan's question, to point out, at least on the ocean side, the autonomous platforms aren't fast and storms are. So we can't chase them down. The best we can do is be out there and a storm comes over us. With, you only get 5 days, something like 5 to 7 days lead time. You can't move an asset more than order 100 kilometers typically, which is not a whole lot. So really, it's about being out. If you want to catch the storms with the autonomous stuff, it's about just being out there and having enough of them out there that some of them will get run over by the thing coming by.
Presumably there's a space between totally stationary and, hypersonic travel. I think they're semi-adaptive, right? It's maybe 10 knots is not world-beating, but it's fast enough that if we're in the general region and we're worried about hitting a region of a storm that's not very energetic, we can nudge it, a couple kilometers. That's more what I was talking about. Because I think there's so many near misses where you miss really interesting dynamics because you're ever so close. And if you were just able to nudge it a little bit, you'd be able to fill in that spot. That's all. But your point is well taken. Thank you.
All right, so I'm going to just moderate. I'll say we'll go to Elizabeth next.
Yeah. Yeah, so Caroline, I don't think you're the only one that cares about the background state to give you some validation. I think I've heard that a lot of background state and perturbed state. And in that vein, I wanted to revisit a way that Roger phrased things that I thought was really useful. He said in his breakout session, using either case studies or just data to evaluate forecast models if they show a strong ocean or ocean evolution effect on the atmosphere. And so I guess I wanted to, I know we don't have a ton of time, but ask more from the audience on how that sort of evaluation of ocean impact on the atmosphere would happen. I know in our group we talked about transports in and out of the boundary layer, and I wondered if anybody else had any thoughts on that. How to test or evaluate models for their evidence of ocean influence on the atmosphere. I guess the other one we talked about was like diabatic heating from presumably convection that comes somewhat from surface effects, and the diabatic heating can imprint on the jet stream, and that's how the wave train is affected. Anything else?
Okay, hey, Chris.
Yeah, this is Chris Zappa. I just have a simple example of that, Elizabeth. When, say, you have a algal bloom or cyanobacteria bloom, and you enhance the near ocean heating, and then you measure the fluxes in that region. Typically, we see enhanced, a significant deviation from core in that case, right? So the ocean heats up, you see the response in the atmosphere right away in terms of you see enhanced sensible heat fluxes over that region. I mean, it's kind of a perturbation on the system, but it's a way some way to observe it. Maybe there are other cases like that you could look at.
Okay, I would say one other bit to add would definitely be just the boundary layer height itself and its variability, checking to see how it corresponds to the SST variability. So then that'd be much more local. And then on the non-local, your point about diabatic heating and downstream, that links in with the schematic that Roger showed at the end of his, where it's it's a teleconnection, isn't it? And then Meghan, did you have more or a follow-on? Or if not, Andrea had her hand up as well.
I did. The slide that Hyodae had given me about the hurricane glider response project, hurricane project, did show that they were able to go and deploy the coordinated glider and sail drones beneath the hurricanes and get good data that was targeted towards those storms. So it has been done, this adaptive sampling. For the sail drone and the glider coordinated together. Not the glider, the glider wasn't. Oh, okay. The sail drone did the storm chasing, and they did do the glider sail drone, but not beneath the hurricane. Okay.
But Jamie said the sail drone was already out there, right? It was like, it was already out there. Well, as Nathan said, it got moved as the track adapted.
Catherine has some follow-on on that.
Yeah, I can speak to that. This is Catherine Edwards. That storm chaser in the week or 10 days as Sam was approaching, Hurricane Sam, not that Sam. It was definitely positioning that sail drone and moving it toward the predicted track, and the positioning where it was chosen to basically be able to intercept on the most common paths of tropical cyclones. So it was placed where it was as a goalie, in a sense.
Okay, great. And then we're going to shift gear maybe with some. Thanks, Andrea.
Yeah, no, this is back to the same topic. I'm just wondering if people think the ones that do the targeted observations, if we had, let's say, subseasonal or seasonal predictions, these multi-model consensus for SST, for temperature and stuff like that are pretty good. So if we had a forecast that a month from now, conditions here are going to be, it's going to be stormier than usual. I'm wondering if it's worth using that kind of stuff to send, and that way you could get background conditions, wait for you don't know exactly what day the storm is going to come, but during that month we're going to have more than usual, so the odds are better. I'm just wondering if something like that is worth, or is that too risky?
I think we just have to ask ourselves, what observations do we really want for this problem? And then ask ourselves, how are we going to get those? And then the next question is, how rapidly, if we decide to make this a hurricane thing, how rapidly can we get those observations out there? I mean, I think it's a question, right? And how expensive will it be? We're sending out planes every time so that we can get some boundary layer information, right? Dropsondes, and then we're sending out, Anyway, it's just, I would say we should ask ourselves, what's the data that we really want to get? How difficult is it to just move that around at will? How expensive will that be, right? I know I like to say, if you have infinite money, like what would you do? Anyway, if you just sit there, storms will come over you. It's like when we were doing spurs in the ITCZ and they kept going, let's chase the rain. You're like, if you just sit here, the rain will come. It's the ITCZ. It's going to rain on you every day. Like, that's just going to happen kind of wherever you are in that part of the Gulf Stream. You're going to have storms coming over you. Now, they might, be of various flavors. You might not catch, one piece of one, that is compared to another, but.
Could we have a sampling strategy that maximized the likelihood that one of the autonomous vehicles would encounter a storm, so that instead of just having bing, 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 they're kind of doing alternating zigzags back and forth. So if a cyclone comes through, it's going to hit one of the four that are deployed.
But again, then my question is, ask yourself, what are the observations that you want to get? Like a sail drone, if the only observation that we have is a sail drone sitting out there, we have nothing about the upper atmospheric boundary layer. But if we have a sail drone and we have a plane dropping things, right, then you start to get that. But are we sending planes? Now we have a plane on standby, and it goes out, right? I'm just saying, that's what you have to, like, what are the observations that we want to have, and how difficult is it to quickly deploy those? Right.
Oh, yeah, but Chris Airall here, I mean, the hurricane program operates that way with the aircraft and with stuff deployed in and on the ocean. And it's like a 5-month thing. And the airplanes are pretty easy because they fly when there's an event to fly on, and they just fly out where the event is. So that's fairly straightforward, and they like being on standby. They can't fly every day for a month. So I don't know what the hurricane program costs for the P3s. It's probably $10 million, including aircraft time and expendables and all that. So if that's what you're after, if you're after mid-latitude cyclones, I think you can just use the hurricane program as a map.
Robert Todd again, and totally, aircraft are totally, really the only, I think, viable rapid response kind of thing. Then you can actually fly out and drop stuff in. The other practical problem with rapid response, and I'm bringing these things up because we spent $5 million of Hurricane Sandy supplemental money years ago to show that rapid response was really not very effective. If you're doing rapid response to a particular storm, you miss the pre-storm conditions because you have 5 days-ish of lead time. It takes you 2 of those to decide you're going to actually go, then another day to get stuff out there, and suddenly you're getting stuff in right before the storm comes by. Ditto for flying into the path of the storm. You're really not getting very much of the pre-storm conditions. So some of the things you might want are like a transect across the Gulf Stream before the storm got there. Then see what happens during the storm, then what's after. And if you're not out there already, waiting for things to come by, you miss that.
But it's easy to target that too. There's no law says the P3s can't fly when the weather's nice. You can, if that's part of your plan, you just put in, I mean, the forecasts are pretty good for like 5 days. You have a rough idea. So I think you could do pre-storm a couple of days ahead of time. Pretty easy.
I was going to say, I disagree with that as well. I am part of the Hurricane Field Program, and part of the Hurricane Field Program does pre-storm ocean observations. They usually do lawnmower flight patterns to observe a pre-storm state, like Chris was mentioning. So it's possible that that is the intent of what you want to do.
Well, I think this is a really good discussion because I think the question is, do we want to do a storm program? Right?
I would say the 2 different discussion groups I was in, it was always we wanted both. It was definitely the case that we wanted persistent measurements and then the possibility of adding in these targets. From what we've talked about just now, I agree with you, Carol Ann, that there's storms over the region are occurring, at least extratropical cyclones are occurring frequently enough in winter that they will pass over stationary assets, and you'll probably sample all different parts of the storms in that way. So I think in terms of coordinating a plan, it's probably easier to have stationary observations. I mean,
if you're there, it's more likely that you're trying to avoid it. You know, like, everyone's always trying to get you to avoid the storm because there are parts of the side when you're right in the big way.
Yeah, so
There's storms. There's always storms. There's a storm. It's a
Jamie
storm
amplifies the point that the storms are there.
It's harder to avoid the storms than to find the storms.
Elizabeth has her hand up.
Oh, unmute. Unmute. She's not muted.
Oh, sorry, we are having IT problems on our side where we can't hear you yet, Elizabeth. Just a moment. I don't know why this is happening.
Elizabeth, go ahead and say something. Okay, no, we still can't hear you.
Okay, sorry, Elizabeth, give me a minute to try to figure this out.
So while you're waiting, Chris again.
Oh, we've got Chris. Okay, good. Go ahead,
big
Chris.
mouth here. I've done a lot of field programs with ships, and you just go out there and sit for a month And they're a little more mobile than sail drones, but at the speed storms move, they're kind of stationary. And you go out and you get, if you're out a month in these conditions, maybe you get 2 or 3 storms go by, and that's, you know, a good sample in a month usually. I don't think we've ever been skunked and haven't gotten any storms. But that doesn't mean you get the whole story from ships or sail drones. So personally, I think they go well. Airplane programs match well with ship programs.
And what about the oleander as a platform? Well, instead of, that would give you a ship that is regular throughout the year. And I don't know whether, you know, we could have somebody on that. I know that they generally like to just have autonomous systems, but for, you know, an intensive sampling, then what if that regular line is a commercial ship as opposed to a research vessel?
Elizabeth, do you want to try speaking again?
Yeah, I think I fixed it, right? Yeah, I was gonna say our rapid response strategy could also apply to enhanced ocean submesoscale activity, or like an interesting or unique Gulf Stream separation event. And I was wondering how fast those evolve, or are we gonna see that all coming, or if that's more or less well sampled by satellite, will we know when to do that? I don't have a good sense of how fast those things move in this part of the Gulf Stream. Does anyone know?
Apparently it's not common knowledge because no one yet has jumped up. Anybody?
I'm guessing that you'd still want all your ocean assets in the water ready, because yeah, as the NASA program manager told me, we do not chase rain. and then you might want to deploy the aircraft in that case, because now the submesoscale ocean activity or the Gulf Stream separation is an interesting case, and we're going to deploy the aircraft so that we can sample the interesting new atmospheric response before and after, during the storm, as we've talked about. This seems just like I don't think that the rapid response is just a mid-latitude cyclone.
So this is Hyodae. I guess submesoscale depends on types of submesoscale eddies, but some mixed layer eddies are very transient, like the lifetime scale of like day or something. It's really small, so I don't think we have a very good understanding of how those submesoscale processes influence boundary layer flux or anything like that. Anything smaller than mesoscale, I'll argue that we don't really understand very well. Or there's some modern evidence of submesoscale imprints on the fluxes, but I don't know how different it is compared to mesoscale coupling that we observe from satellite. I think scales are much smaller in time scale and spatial scale, which is much harder to estimate from even aircraft measurement, but yeah.
I'm not totally sure which kind of features that you mean, because there's like a bunch in that list, but a counterpoint to this idea that they develop fast and decay fast is that they are predictable where they develop and decay, which is at the edges of mesoscale features. And the mesoscale features are super visible from space and slow moving and slow to decay. And so if that was the thing of interest, if that was what someone decided was the thing of interest, it would definitely be, in my view, it would be very feasible to go to the edge of a mesoscale feature where you will find submesoscale features and be there and ready. I don't know if that's the...
That sounds great. So you'd be basically adaptively sampling around a mesoscale feature, waiting for submesoscale apples to fall off the tree with your autonomous vehicles.
Do other people agree? That seems reasonable to me. Yeah.
So I think just to bring it back to a point that Elizabeth made, that we started talking this morning, like what, fortunately, especially for those of you who are just starting out in this field, there are a ton of questions that we have not yet answered that will take your entire career probably to figure out how to answer, which is great for you. You'll be relevant for quite a while on this. But I do think it's worth saying there are a very large number of questions that one could come to, and there's a very large number of scales. And so Elizabeth's comments this morning and, or just now, and what we talked about this morning is, there's all different ways to get at various things. I think the starting place is to ask what things are we trying to, what are we trying to understand, right? Because, yeah, we can get to sub-mesoscale, and that's, that will be really important if we decide that what we really need to know in this region is the sub-mesoscale air-sea coupling. There's ways to get to that. Is it the S2S and sort of the impact of storms and sort of that? Well, that's a different question from which we derive hypotheses that guide us towards what kind of modeling, what questions do we have, what modeling do we need, what observations do we need. And so I think it's useful asking ourselves, all the different things that we could see. I think the question is what, where are we going with the hypotheses, and then saying, what do we need from this? Like he just left. He knew it. He knew I was about to call on Reese. But I was just going to say, then, if we're looking at this, then Reese, what are the observations, for instance, that, since you look at this all the time, what observations do you need? But Larry, you had a question. Where's the mic?
John, sorry.
Did John have one?
John Bain is raising his hand.
Okay, go, John.
Can I be heard at the moment? I've had audio problems all day.
Yes, you can be heard.
Great. I'll try to get this in before my audio goes out. I want to second Chris's comment about ship and aircraft joint operations. These work extremely well in certain conditions. There was a question a little bit earlier about what does a shift in separation event look like where the Gulf Stream is separating from Cape Hatteras, and I think that there's not a clear answer to that in the physical oceanographic community. The other thing that I want to encourage this group to do is to get a good description, maybe a summary document or something like that, of the range of known Gulf Stream frontal variations. Meanders and frontal eddies and filaments and that sort of thing are quite well known. And that's the Gulf Stream mesoscale. Those are order 100 kilometers. And it occurs to me that part of the discussion here should recognize that I think the atmospheric mesoscale is 1,000 kilometers, if you want to consider cyclones a mesoscale feature compared to global scale. So there's quite a scale mismatch. There's certainly a mismatch in transit speeds. Extratropical cyclones go quickly. Gulf Stream meanders take an entire week to go 100 kilometers. Sort of looking at what's known in those two categories, the atmospheric mesoscale, the oceanic mesoscale in the Gulf Stream region, I think that would be somewhat enlightening and help guide how observational programs along the lines that are being discussed here could be designed.
Larry, you've had your hand up for a bit. Do you have a mic? Okay.
I just wanted to go back.
Turn it on, though. Is it on?
Yes.
Okay. Be assertive.
Go back to the sub-mesoscale question, and I guess it would be my preference not to deal with that. And the reason is because, so I was part of the SBOAT program. It's a sub-mesoscale ocean dynamics experiment. And so we had a study area off the coast of California around San Francisco, and we had this polygon-shaped study area about, roughly 75 miles by 75 miles, but it was kind of shaped strangely. And we had aircraft, sail drones, a bunch of autonomous vehicles and things like that. And I was on the ship doing radiosonde and meteorological measurements to look at sub-mesoscale air-sea interaction. And the barriers we had to it were the fact that finding submesoscale features was a lot harder than you would think. So we were relying quite a bit on sail drones and things and AUVs to map out kind of the mesoscale area, doing a mesoscale survey, and then going to where we thought there was submesoscale stuff. And the reason why we couldn't see it from satellites is because it's cloudy a lot of the time. Off San Francisco in October, it's like 80% of the time is cloud covered. Over the Gulf Stream in winter, it's over 90%. So you're probably not going to get any help from satellite imagery to try to identify submesoscale features in which to launch an invasion of, to get to it. So you won't get to the submesoscale feature in time. And that's actually what happened to us, is we would chase around stuff on the ship, and by the time we got there, there was, the evolution of the feature was, quite a bit to what we thought it was going to be. And the second thing is, I think that, from the data I got, and, the submesoscale coupling to the atmosphere, it's a little bit weak, and it really depends on, how strong the feature is and things like that. So you can actually consider it like this: the north wall of the Gulf Stream is a submesoscale feature because its cross-frontal length scale is 5 kilometers. And so that would technically be a submesoscale feature. But we think about it as a mesoscale feature because it's a long frontal length scale. But anyway, so I would really like to, focus a little bit more on those length scales. And those submesoscale, I think, would add just another dimension that, we wouldn't, I don't know how much. I mean, I think there's a lot more to learn at the mesoscale. With that, my 2 cents.
Does anybody want to talk about the atmosphere and ocean mesoscale thing? Justin does? Justin.
Yeah, I was just going to second Larry's view. I've seen some papers on the influence of submesoscale on the atmosphere, and I think it's very sensitive and case dependent. The one paper I'm thinking of did a number of experiments, and it only really had an impact on the atmosphere when the background wind was nearly zero. But once you increase the background wind, I think the boundary layer wasn't seeing so much of the submesoscale feature. That's just one modeling study. Then maybe there's others that say different things, but coupled with what Larry is saying about the difficulty of measuring it, I'm kind of inclined to agree with Larry that maybe looking at the larger features. And also in one of our breakout sessions, we made exactly the same point that Larry did about the north wall being a very sharp front, which is submesoscale in scale, but it's on the edge of a mesoscale feature. Maybe that's more interesting than isolated vortices of submesoscale, because they just take a very small surface area of the ocean, and maybe the atmosphere doesn't feel that. But the long coherent edge of the Gulf Stream, even though it's narrow in one side, the long coherence in the other direction might mean it has more of an effect. So that aspect be of more interest to me than small isolated vortices. So that was my thoughts on that. But people might be able to argue against that.
Elizabeth, is this a new hand up?
Yeah, I was just going to say that's all really helpful in clarifying order of importance and priority. And so I'm hearing that mesoscale ocean features would be, and or their sharp fronts, or like those mesoscale or eddy meander, like the larger scale features that are more persistent, obviously having more opportunity for influence. I just want to clarify with like maybe Luann, if she's still here, because I know that we talked to, or like anyone else in my groups, that we stressed the submesoscale ocean. Does that still capture the unknowns about ocean dynamics? I know that we mentioned like strong vertical velocities on submesoscales, and I don't know if that's the same thing, like, oh, those aren't the little vortices, those are the edges of the fronts. Are we all talking about the same thing actually, or?
That's what I was talking about.
Okay.
It may not be what I'm thinking, that where the fronts are strong. I was thinking of that as submesoscale as opposed to sort of quasi-geostrophic scale. So I think it's consistent.
then that's what I tried to say. And that didn't come across, but I'm really glad we had this to clarify. Thanks.
All right, did I see another hand up? Is there anyone online with a hand up? I'm not seeing anyone. Okay, well, we're just about at the end of our day here. And if you're, if you're on the West Coast, this will also probably feel like time for wine for you too, if you've been on with us 8 hours. So today we're ending. Tomorrow morning, again, 8 o'clock, we'll try to have a synopsis of day 2 and a discussion, and we'll do another breakout session, which is maybe talking a little bit about what are we going to do with this moving forward. So, think about that a little bit, because I think we've asked a lot of questions. We maybe have gotten a little bit of clarity on what we may or may not want to do, but there's a lot of where do we go from here. I'll just give you one example that was mentioned to me, and I think Andrea, you were the one who said it. For instance, it would be useful to have a POR section, like a what data is actually out there currently, because we're probably not taking advantage of the data that is out there, and it would be useful just to sort of have that as a thing, here are buoys, here's satellite data, here's, all the different, here's different experimental, things. And that includes upcoming ones. So, the online group that had that, that would be really useful for. And is there anything, Sam, that you want to add?
If Carol Ann is through, the virtual people, you're free to go, so to speak.